Hello, good evening, and welcome to The Sleepy Scientist. It's genuinely lovely to have you here. Tonight we're exploring the quantum experiments that changed everything. Might I ask one small thing first? If these videos are something you treasure, our ebook may be just your sort of thing, and it lives over on the Sleepy Scientist website. It's a full ebook with a complete narrated version alongside it, so you can read or simply listen, whichever suits the evening. Look for the QR code on screen across the opening 5 minutes, and the sleepyscientist.com sits in the description for whenever the time feels right. Your support really is the thing that keeps this channel alive, and the reason I'm able to carry on making these videos at all. For that, quietly and enormously, thank you. Before we go any further, I'd love to know where in the world you're watching or listening from tonight. One of my favourite things about making these videos is seeing just how far they travel, reaching people in different towns, different countries, and sometimes completely different time zones, all settling down to explore the same quiet corner of science. Quantum physics is often introduced through strange ideas, particles behaving like waves, energy arriving in discrete amounts, atoms occupying several possibilities at once, and distant objects sharing connections that seem to ignore ordinary intuition. But these ideas weren't invented simply because physicists wanted the universe to seem mysterious. They emerged because experiments kept producing results that the older laws of physics could not explain. From the faint glow of heated objects and electrons released by light, to particles passing through two slits, atoms splitting into separate beams, and entangled photons tested across great distances, each experiment removed another piece of the familiar classical picture. Slowly, and often reluctantly, physicists were forced to accept that nature behaves very differently at its smaller scales. So make yourself comfortable, allow the day to grow a little quieter, and let us begin with the experiments that revealed the quantum world. By the closing decades of the 19th century, physics appeared to be approaching something close to completion. The universe seemed to operate according to a small collection of powerful and dependable laws. There were still unanswered questions, certainly, but many scientists believed that the basic framework was already in place. What remained was largely a matter of improving measurements, filling in missing details, and applying familiar principles with greater precision. Newtonian mechanics described the motion of falling stones, orbiting planets, swinging pendulums, and machinery on Earth. Isaac Newton's laws had survived centuries of increasingly careful tests, and they gave physicists a clear picture of matter as solid objects moving along definite paths through space and time. Thermodynamics explained heat, work, temperature, engines, and the broad statistical behaviour of enormous numbers of particles. Its laws placed firm limits on what machines could achieve and explained why heat naturally flowed from hotter objects toward colder surroundings. James Clerk Maxwell's electromagnetic theory brought electricity, magnetism, and light into one elegant system. Maxwell showed that changing electric fields generate magnetic fields, while changing magnetic fields generate electric fields. These linked disturbances could travel through space as electromagnetic waves, moving at the measured speed of light. Light itself appeared to be an electromagnetic wave, joining optics to electricity and magnetism in one remarkable achievement. Taken together, these theories seemed capable of explaining almost every known physical process. Matter consisted of particles. Light consisted of waves. Energy flowed continuously. Objects possessed definite properties whether or not anyone happened to measure them. The universe might be complicated, but it did not appear fundamentally unreasonable. Then the experiments began to misbehave. The warning signs did not arrive as one spectacular discovery. They appeared gradually, scattered across different laboratories and different areas of physics. Heated objects produced patterns of light that classical calculations could not explain. Individual chemical elements emitted sharply defined colours, rather than every possible colour. Light striking certain metals could release electrons. but the result depended on the colour of the light in ways that ordinary wave theory struggled to describe. Even the atom itself presented a serious problem. According to classical electromagnetic theory, an electrically charged electron moving around an atomic nucleus should radiate energy. As it lost that energy, it should spiral inward rapidly and collapse into the nucleus. Stable atoms should not have lasted for long enough to assemble a table, a laboratory, or the physicist attempting to calculate their collapse. Yet atoms were plainly stable. These puzzles mattered because physics depends on a continuing conversation between theory and experiment. A scientific theory is not simply a guess. It is an organised framework that explains observations, connects different phenomena, and produces predictions that can be tested. A good theory may reveal that events which look unrelated are expressions of the same underlying principle. An experiment performs a different role. It asks nature a carefully arranged question. The answer may support a theory, place limits on it, or reveal that something important is missing. No matter how beautiful a theory appears, it must remain connected to measurable reality. That connection was particularly difficult to establish in the early quantum experiments. The researchers involved did not have digital detectors, automated data analysis, or computers capable of correcting every wobble in the apparatus. Many worked with fragile glass vacuum tubes assembled by hand. Their vacuum pumps left far more gas inside an experimental chamber than modern systems would tolerate. Electrical currents could be extremely weak, while unwanted vibrations, temperature changes, dust, and electrical interference could distort delicate measurements. Light sources were often unstable. Photographic plates had to be exposed, developed, and examined. Detectors sometimes consisted of small metal surfaces connected to sensitive instruments whose needles moved only slightly. A loose connection or contaminated sample could quietly spoil hours of work. The universe was already being uncooperative, and the equipment occasionally joined in. Despite these obstacles, the experimental results became increasingly difficult to dismiss. Energy did not always behave as a perfectly continuous quantity. Matter did not remain purely particle-like, and light did not remain purely wave-like. Atoms possessed discrete energy states. Electrons displayed intrinsic spin, a quantum property with no exact classical equivalent. Quantum systems could exist in superpositions, combining several possible outcomes within one mathematical state. Entanglement revealed that two systems could share correlations that could not be explained by assigning each of them a completely independent set of local properties. Measurement itself became part of the physical description, because extracting information required an interaction that could alter the state being measured. Individual outcomes often remained unpredictable even when the statistical pattern across many trials could be calculated with extraordinary accuracy. These ideas are sometimes presented as though a group of physicists simply decided to make reality strange. In fact, many of the scientists responsible for quantum theory were uncomfortable with its implications. They did not abandon classical physics casually. Classical physics worked too well across too many areas to be discarded without overwhelming evidence. Quantum mechanics was forced into existence because experiment after experiment pointed toward the same conclusion. The older framework was not wrong in every situation. It remained an excellent approximation for planets, machines, falling objects, and most events at ordinary scales. But it was not the deepest available description of nature. The evidence began with heated matter, emitted light, and electrical currents. It eventually reached individual electrons, isolated atoms, entangled particles, superconducting circuits, and carefully controlled units of quantum information. Instruments became more precise, yet the underlying message remained consistent. At microscopic scales, nature did not obey the simple classical picture that had once seemed so secure. Physicists now agree to astonishing precision about how quantum mechanics predicts experimental results. The mathematical framework has guided technologies ranging from lasers and transistors to magnetic resonance scanners and atomic clocks. Yet disagreement continues over what the framework ultimately says about reality. The calculations are dependable, the experiments are repeatable, the interpretation remains unsettled. That combination is part of what makes quantum physics so unusual. It is not a vague mystery resting beyond the reach of evidence. It is one of the most thoroughly tested structures in science, built from experiments that repeatedly showed that the familiar world was resting upon rules far stranger than anyone had expected. One of the first signs that classical physics was reaching its limits came from something remarkably ordinary: the glow of a hot object. A metal bar placed in a furnace begins by radiating mostly invisible infrared energy. As its temperature rises, it develops a faint red glow. With further heating, the colour shifts toward orange, then yellow, and eventually a brilliant white. The object is not changing colour in the usual sense. Instead, the pattern of electromagnetic radiation leaving its surface is changing with temperature. This behaviour was familiar to blacksmiths, metalworkers, glassmakers, and anyone who had watched the coals of a fire. Yet behind that simple glow was a problem that the best physics of the 19th century could not solve. To study thermal radiation cleanly, physicists developed the idealized concept of a blackbody. A perfect blackbody absorbs all electromagnetic radiation that falls upon it. It reflects none of the incoming light and allows none to pass through. When heated, it emits radiation with a spectrum determined almost entirely by its temperature. No real material is a perfect blackbody, but a hollow container with a small opening provides an excellent approximation. Radiation entering the opening reflects repeatedly from the internal walls and has very little chance of escaping again. The small hole therefore behaves almost like an ideal absorber. When the container is heated, radiation emerging through that opening reveals the characteristic spectrum of a blackbody. This arrangement allowed physicists to study thermal radiation without becoming too distracted by the chemical details of the material itself. Iron, ceramic, and other substances might differ greatly at lower temperatures, but an ideal blackbody offered a universal pattern. The question was no longer merely why a particular piece of metal glowed. It was why heated matter everywhere followed the same underlying law. During the late 19th century, this became an increasingly precise experimental problem. At the German Imperial Physical Technical Institute in Berlin, researchers including Otto Lummer, Ernst Pringsheim, Heinrich Rubens, and Ferdinand Kuhlbaum developed improved blackbody cavities, sensitive detectors, and methods for measuring radiation across a wide range of wavelengths. Their work was demanding. Infrared radiation is invisible, so the measurements could not be made by simply looking through a prism and writing down the colours. The researchers had to separate radiation by wavelength, detect tiny heating effects, control the temperature of their apparatus, and account for energy absorbed by the surrounding equipment. The measured spectrum had a clear shape. At any fixed temperature, the emitted intensity rose with increasing frequency, reached a peak, and then fell away. Hotter blackbodies emitted more energy overall, and the peak moved towards shorter wavelengths. This is why a moderately heated object glows red while a much hotter object appears yellow or white. Classical physics could describe parts of this pattern, but not the whole thing. Wilhelm Wien found a formula that matched the measured spectrum well at shorter wavelengths and higher frequencies. Wien's law also correctly described how the peak of the spectrum shifted as temperature changed. His work was a major success, but increasingly accurate measurements at longer wavelengths reveal that his formula did not remain correct across the full range. Another classical approach, associated with John William Strutt, better known as Lord Rayleigh, and later refined by James Jeans, worked reasonably well at longer wavelengths, yet it produced a disastrous result at shorter wavelengths. According to this calculation, a heated object should emit more and more energy as the wavelength became shorter. The predicted energy did not merely become large, it increased without limit. Taken literally, Every warm object should have released an impossible flood of high-frequency ultraviolet radiation. Real objects did nothing of the kind. A heated oven did not quietly destroy the room with infinite ultraviolet energy, which was considerate of it, but deeply inconvenient for the theory. This failure later became known as the ultraviolet catastrophe. The name was dramatic, but the problem was genuine. Classical theory treated the electromagnetic modes inside the cavity as though each could take any amount of energy continuously. Because there were more available modes at higher frequencies, the total predicted energy diverged. Max Planck approached the problem cautiously. He was deeply committed to thermodynamics and did not begin by trying to overthrow classical physics. His immediate goal was to find a formula that matched the excellent experimental measurements. In October of 1900, after learning about new long-wavelength results from Heinrich Rubens and Ferdinand Kuhlbaum, Planck produced an expression that accurately connected the regions described by Wien's law and the classical long-wavelength behaviour. It matched the observed blackbody spectrum across the full measured range. Finding the formula was only part of the challenge. Planck then needed to explain why it worked. In December of 1900, he presented a derivation built around an extraordinary assumption. He treated the oscillating matter in the walls of the blackbody cavity as though it could exchange energy with the electromagnetic radiation only in discrete amounts. The size of each allowed energy packet depended on the frequency. Higher frequency oscillations exchanged energy in larger packets, while lower frequency oscillations used smaller packets. The relationship can be stated in words as follows. The energy of one quantum equals Planck's constant multiplied by the frequency. Planck's constant is extraordinarily small. Its value is roughly 6.63 multiplied by 10 raised to the power of negative 34 joule-seconds. Written as an ordinary decimal, it contains 33 zeros after the decimal point, before the first significant digit appears. Because this constant is so tiny, the spacing between allowed energy amounts is usually undetectable in everyday objects. A swinging pendulum, a moving vehicle, or a warming cup of tea exchanges energy in quantities so enormous compared with a single quantum that the process appears continuous. At atomic scales, however, the packets become impossible to ignore. For light with a high frequency, even one quantum can carry a meaningful amount of energy compared with the energies inside an atom. The apparent smoothness of the everyday world begins to break into discrete steps. Planck initially regarded this quantization as a mathematical necessity, rather than a literal description of nature. He had discovered a method that reproduced the measurements, but he was reluctant to claim that energy itself truly arrived in indivisible packets. The assumption seemed too strange and too far removed from the continuous processes of classical physics. That reluctance is understandable. Quantization was not a modest correction to an existing calculation. It suggested that nature placed restrictions on which energy exchanges were allowed. Classical intuition said that an oscillator should be able to gain or lose any amount of energy whatsoever. Planck's results said that only particular increments were available. The historical irony is that Planck introduced energy elements while trying to preserve as much of classical physics as possible. Instead, his solution opened the first clear doorway into quantum theory. The blackbody experiments did not yet reveal photons, electron waves, spin, or entanglement. They established something more basic and just as unsettling. At sufficiently small scales, energy could not always be divided smoothly into any amount one pleased. Nature appeared to count, and once that possibility entered physics, the continuous world described by 19th century theory could never again be regarded as the complete story. The first clear hint that light could behave as something more than a continuous wave appeared during experiments that were originally designed to investigate electricity. In the late 1880s, Heinrich Hertz was studying the production of electromagnetic waves. His work provided powerful confirmation of James Clerk Maxwell's theory, showing that electrical disturbances could travel through space with the properties expected of light. During these experiments, Hertz noticed an unusual detail. electrical sparks crossed a gap more easily when ultraviolet light illuminated the metal electrodes. The effect seemed minor beside the successful detection of electromagnetic waves, but it pointed toward a much deeper puzzle. Light was somehow helping electrical charge escape from matter. Wilhelm Hallawax explored the phenomenon further. He found that ultraviolet light could cause a negatively charged metal surface to lose its charge. Philippe Lenard later carried out more systematic experiments using evacuated glass tubes, illuminated metal surfaces, and electrical fields that allowed the emitted particles to be collected and measured. By this time, the electron had been identified as a negatively charged component of matter. The particles leaving the metal under illumination were therefore understood to be electrons. The process became known as the photoelectric effect. At first, classical electromagnetic theory appeared to offer a straightforward explanation. Light was a wave carrying energy through space. When the wave struck the metal, its electric field could shake the electrons inside. Given enough transferred energy, some electrons might eventually escape from the surface. This picture produced several reasonable predictions. A brighter light wave carried more energy, so increasing the intensity should give the electrons more energy. Even low-frequency light should eventually release electrons if it was bright enough or allowed to shine for long enough. If the wave delivered energy gradually, there might also be a measurable delay while an electron accumulated the amount needed to escape. The experiments gave very different answers. For each metal, there was a threshold frequency. Below that frequency, no electrons were emitted, regardless of how intense the light became. A powerful red light could shine on certain metal surfaces without releasing any electrons at all. Making the red light brighter did not solve the problem. Leaving it on for longer did not help either. The electrons were apparently unimpressed by patience. When the frequency rose above the threshold, electrons were emitted almost immediately, even if the light was weak. There was no significant waiting period during which energy slowly accumulated. The response occurred far too quickly for the simplest classical picture. Increasing the intensity of suitable light did increase the number of emitted electrons. It did not, however, determine the maximum energy carried by each electron. That depended mainly on the frequency of the light. These results created a sharp distinction between intensity and frequency. Intensity describes how much light energy arrives across a given area during a given time. Frequency describes how rapidly the electromagnetic field oscillates and is closely related to the color of visible light. Classical wave theory concentrated energy into greater intensity. The experiments seemed to concentrate energy according to frequency. Albert Einstein offered a solution in 1905. Max Planck had already introduced discrete energy elements to explain blackbody radiation, but Planck had applied quantization to the exchange of energy between matter and radiation. Einstein took the idea much further. He proposed that light itself behaved during emission and absorption, as though its energy were concentrated into localized packets. These packets later became known as photons. The energy carried by each photon depended on the frequency of the light. The relationship can be stated as follows. The energy of a photon equals Planck's constant multiplied by the frequency of the light. A higher frequency photon therefore carries more energy than a lower frequency photon. Ultraviolet photons carry more energy individually than visible red photons, even when the red light is extremely bright. Einstein pictured the photoelectric effect as an interaction between one photon and one electron. A photon transfers its energy in a single event. Part of that energy is required to free the electron from the metal. This minimum amount is called the work function, and differs between materials because electrons are bound with different strengths. Any energy remaining after the electron escapes becomes kinetic energy, the energy associated with its motion. The maximum kinetic energy of the emitted electron equals the photon energy minus the work function of the metal. This immediately explains the threshold frequency. If one photon does not carry enough energy to overcome the work function, No electron can escape through the ordinary photoelectric process. Supplying more low-frequency photons increases their number, but it does not increase the energy carried by any individual photon. Once the frequency rises above the threshold, each suitable photon can release an electron. Increasing the light intensity then sends more photons toward the surface and can produce a larger electrical current because more electrons are emitted. Raising the frequency gives each photon more energy and increases the maximum kinetic energy of the released electrons. The explanation was simple, but its implications were radical. Maxwell's wave theory of light had been one of the greatest achievements of classical physics. Interference and diffraction experiments had shown beyond reasonable doubt that light displays wave behaviour. Einstein was not denying those results. He was showing that a purely continuous wave description could not explain every interaction between light and matter. Robert Millikan subjected Einstein's proposal to an exceptionally careful experimental test. Between roughly 1912 and 1915, Millikan measured the photoelectric effect across several metals and frequencies. He used a variable opposing voltage to prevent the fastest emitted electrons from reaching a collecting electrode. The stopping voltage revealed their maximum kinetic energy. Millikan was initially skeptical of Einstein's light quantum. Nevertheless, his measurements confirmed the predicted linear relationship between light frequency and electron energy with impressive precision. The slope of that relationship provided direct measurement of Planck's constant, while the threshold varied according to the work function of the chosen metal. The experiment confirmed Einstein's equation, even though Millikan remained reluctant to accept the full physical interpretation immediately. Science occasionally has the pleasant habit of allowing an experimenter to verify an idea he would rather not believe. The photoelectric effect did not prove that light is an ordinary stream of tiny classical balls. Photons are quantum excitations of the electromagnetic field, and their behaviour cannot be captured completely by either a traditional particle picture or a traditional wave picture. Light can produce localized transfers of energy while also generating interference patterns associated with waves. What the experiment established was that electromagnetic energy is exchanged through individual quantum events. Matter does not always absorb light in a smooth and continuously divisible flow. That principle now operates throughout modern technology. Photodetectors convert incoming photons into electrical signals. Digital cameras use arrays of light-sensitive elements to form images. Solar cells absorb photons and release charge carriers that generate electrical current. Automatic doors, smoke detectors, optical communication systems, and astronomical instruments all depend on related interactions between light and matter. A curious effect observed beside a spark gap had revealed something fundamental. Light could spread and interfere like a wave, yet deliver energy in discrete localized amounts. The classical boundary between waves and particles was beginning to dissolve, and nature was showing that it had never been obliged to respect that division in the first place. Long before physicists could see the internal structure of an atom, atoms were already revealing themselves through light. When a dense solid is heated until it glows, it usually produces a broad, continuous spectrum. Passing that light through a prism or diffraction grating spreads it into an unbroken band of colours. Red blends into orange, orange into yellow, and the visible sequence continues without sharp gaps between one colour and the next. A glowing gas behaves very differently. When an electric current passes through a thin gas, or when the gas is heated enough to excite its atoms, the emitted light does not usually form a continuous rainbow. Instead, it appears as a collection of narrow, sharply defined lines. Each line corresponds to one particular wavelength of light. Much of the spectrum remains dark, while only a small number of precise colours appear. Hydrogen, for example, produces a recognizable set of visible lines, including a bright red line and several lines in the blue and violet regions. Sodium is famous for an intense yellow glow. Mercury produces its own distinctive arrangement of violet, blue, green, and yellow lines. These patterns are known as emission spectra and every chemical element has a characteristic spectral signature. The first major clues appeared through observations of sunlight. In the early 19th century, Joseph von Fraunhofer examined the solar spectrum with improved optical instruments and mapped hundreds of narrow dark lines crossing the otherwise continuous band of colours. These lines became known as Fraunhofer lines. Fraunhofer measured their positions with great care, although their physical origin was not yet clear. Several decades later, Gustav Kirchhoff and Robert Bunsen showed that hot gases emit light at specific wavelengths, and that cooler gases can absorb those same wavelengths from light passing through them. This provided an explanation for the dark lines in the solar spectrum. The hot interior of the Sun produces a broad range of wavelengths. As this light travels through cooler gas in the Sun's outer layers, atoms absorb particular wavelengths, leaving dark gaps in the observed spectrum. Kirchhoff and Bunsen demonstrated that the line pattern could identify the element responsible. Spectroscopy therefore became a method of chemical analysis. Scientists could discover what distant stars contained without collecting a sample, which was fortunate since the delivery arrangements would have been rather inconvenient. The regularity of atomic spectra was obvious, but its cause remained mysterious. Classical physics offered no convincing reason why atoms should emit only selected frequencies. An electron orbiting inside an atom was expected to radiate across a broad and changing range as it lost energy. The observed lines were far too precise for that picture. Hydrogen provided the simplest and most important example. In 1885, Johann Balmer discovered a mathematical pattern linking several visible hydrogen lines. His formula accurately predicted their wavelengths, although it did not explain why the pattern existed. Johannes Rydberg later developed a more general relation that organized additional groups of spectral lines. The Rydberg formula showed that the inverse wavelengths of hydrogen lines followed simple numerical differences. Nature was clearly arranging atomic light according to a hidden structure. The formulas worked remarkably well, but at first they were closer to carefully discovered patterns than complete physical explanations. In 1913, Niels Bohr proposed a model of the hydrogen atom that combined Ernest Rutherford's small, positively charged nucleus with Max Planck's quantum idea. Bohr suggested that an electron could occupy only certain allowed stationary states around the nucleus. In these stationary states, the electron did not continuously radiate energy, despite the expectations of classical electromagnetism. Each allowed state possessed a particular energy. The electron could move between states, but it could not settle at an arbitrary energy between them. When an atom changed from a higher energy state to a lower energy state, it emitted a quantum of light. When it absorbed the correct amount of energy, it could move from a lower state to a higher one. The relation can be stated in words. The energy of the emitted or absorbed light equals the difference between the two atomic energy levels. Because only particular energy levels were allowed, only particular energy differences were possible. Each difference produced a photon with a definite frequency, and therefore a definite spectral line. Bohr's model explained the main structure of the hydrogen spectrum with striking success. It also produced a theoretical expression for the Rydberg constant that agreed closely with measured values. For the first time, the strange mathematical regularities of atomic light appeared to follow from discrete internal energies. The model was not a complete description of the atom. It worked best for hydrogen and for ions containing only one electron. It struggled with atoms containing several interacting electrons, with subtle splitting of spectral lines, and with the full effects of magnetic and electric fields. Later quantum mechanics replaced Bohr's definite electron orbits with wave functions and orbitals. Even so, the central insight survived. Atomic energy is quantized. Electrons in bound atoms do not possess every conceivable energy. They occupy discrete states. Spectroscopy offered strong evidence for this idea, but physicists also wanted to examine atomic energy through a very different kind of experiment. In 1914, James Franck and Gustav Hertz studied collisions between electrons and mercury atoms. Their apparatus contained mercury vapour inside a glass tube. A heated cathode released electrons, which were then accelerated by an adjustable electric potential. After passing through the vapour, the electrons travelled toward a collecting electrode, producing a measurable current. At low, accelerating energies, the electrons collided with mercury atoms but transferred very little energy to them. These were mainly elastic collisions, rather like small objects bouncing without losing much of their motion. As the accelerating potential increased, more electrons reached the collector and the current generally rose. Then something unusual happened. When the electrons acquired approximately 4.9 electron volts of energy, the current dropped sharply. As the accelerating potential increased further, the current rose again, then dropped once more. This pattern repeated at roughly regular intervals. The repeated decreases showed that the electrons were losing energy in specific amounts. Below the required energy, a mercury atom could not absorb an arbitrary smaller fraction through an inelastic collision. Once an electron reached approximately 4.9 electron volts, however, it could transfer nearly that entire amount to the atom, leaving itself with too little energy to overcome the small opposing voltage near the collector. The mercury atom had entered an excited state. It later returned to a lower energy state and emitted ultraviolet radiation with a wavelength of roughly 254 nanometers. The photon energy matched the amount lost by the colliding electron. This created a direct connection between collision energy and emitted light. Electrons supplied energy to mercury atoms in discrete quantities, and the atoms released corresponding quanta of radiation when they relaxed. The Frank-Hertz experiment was initially interpreted within the developing atomic theory of the period, and the exact identification of the mercury states required later refinement. Its central result nevertheless remained clear. Atoms did not absorb collision energy continuously. They accepted particular amounts determined by the spacing between their internal energy levels. Spectroscopy had revealed those levels through the colours atoms emitted and absorbed. The Frank-Hertz experiment reached the same conclusion by measuring the energy lost by electrons during collisions. Two entirely different experimental methods were therefore pointing toward the same structure. Atomic energy came in definite levels, and transitions between those levels governed both the absorption and emission of light. The coloured lines of glowing gases were no longer merely attractive patterns. They were measurements of the hidden architecture inside matter. Atoms had begun to reveal that their internal world was arranged not as a smooth slope of possible energies, but as a quiet sequence of permitted steps. Einstein's explanation of the photoelectric effect had shown that light could transfer energy in discrete packets. Even so, many physicists remained uncomfortable with the idea that light itself possessed an indivisible quantum character. Their hesitation was understandable. James Clerk Maxwell's electromagnetic theory described light as a wave with extraordinary success. Interference, diffraction, polarization, and reflection all followed naturally from the wave picture. The photon proposal seemed to threaten one of the most reliable theories in physics, so researchers searched for ways to explain apparently particle-like effects without abandoning continuous electromagnetic waves. A decisive challenge arrived through experiments involving X-rays. X-rays are a high-frequency form of electromagnetic radiation, with wavelengths far shorter than those of visible light. Because each X-ray quantum carries considerable energy, X-rays can penetrate matter and interact strongly with electrons inside atoms. During the early 1920s, Arthur Holly Compton directed beams of X-rays onto materials such as graphite. Carbon was useful because some of its electrons were weakly bound enough to behave approximately like free particles during energetic collisions. Compton measured the radiation emerging from the target at different angles. Classical electromagnetic theory predicted that the incoming wave would drive electrons into oscillation. Those electrons would then radiate electromagnetic waves at the same frequency as the original X-rays. The scattered radiation might travel in different directions, but its wavelength should remain essentially unchanged. The experiment revealed something more complicated. Some of the scattered X-rays did retain their original wavelength. These were associated mainly with interactions involving tightly bound electrons or entire atoms. Another part of the radiation emerged with a longer wavelength than the incoming beam. More importantly, the size of this wavelength increase depended systematically on the scattering angle. Radiation scattered through a small angle showed only a modest shift. Radiation scattered more sharply displayed a larger one, reaching its maximum when it travelled back toward the source. This pattern could not be explained naturally by treating the X-rays only as classical waves. Compton instead used Einstein's photon idea. He treated the interaction as a collision between an incoming photon and an electron. The photon carried energy, but it also carried momentum. Momentum is normally associated with moving objects that possess mass. A photon has no rest mass, yet special relativity allows it to carry momentum because it carries energy. The relationship can be stated in words. The momentum of a photon equals its energy divided by the speed of light. Because photon energy also depends on frequency, shorter wavelength light possesses greater momentum than longer wavelength light. During a Compton scattering event, the incoming photon strikes an electron and transfers part of its energy and momentum. The electron recoils, while the photon leaves in another direction. Since the outgoing photon now carries less energy, its frequency is lower and its wavelength is longer. The exact wavelength change follows from conserving both energy and momentum during the collision. It depends on the electron's mass, Planck's constant, the speed of light, and the angle through which the photon is scattered. The relationship can be expressed in words. The change in wavelength equals the Compton wavelength of the electron multiplied by 1 minus the cosine of the scattering angle. The Compton wavelength of the electron is approximately 2.43 trillionths of a meter. This is extremely small by everyday standards, but it is easily significant when compared with the short wavelengths of X-rays. Compton's measurements match this quantum collision model remarkably well. Peter Debye developed a closely related theoretical treatment independently, adding further support to the interpretation. The result extended the photon concept beyond energy transfer. The photoelectric effect had shown that light delivers energy in individual interactions. Compton scattering showed that those interactions also involved definite transfers of momentum. A photon could therefore behave like a participant in a collision, obeying the conservation laws normally applied to material particles. Some physicists still wondered whether energy and momentum might only be conserved statistically. Perhaps individual events behaved irregularly, while the correct totals emerged only after averaging many interactions. Experiments by Walter Bothy and Hans Geiger helped settle this question. They used coincidence measurements to detect the scattered radiation and recoiling electrons associated with the same interactions. Their apparatus recorded whether signals appeared at corresponding detectors at nearly the same time. The observed coincidences supported the idea that each scattering event linked one outgoing quantum of radiation with one recoiling electron. Energy and momentum were conserved within individual interactions, not merely across a large collection of unrelated events. This was an important conceptual shift. Quantum theory was not simply describing average exchanges spread smoothly through matter. It was identifying discrete physical events in which particular amounts of energy and momentum changed hands. The Compton effect also connected quantum physics directly with Albert Einstein's special theory of relativity. The photon's energy and momentum had to satisfy relativistic relationships, while the electron's motion after the collision also required relativistic treatment when its speed became sufficiently high. Quantum theory and relativity were no longer separate curiosities. They were beginning to meet within the same laboratory measurements. Describing the process as a photon collision does not mean that a photon should be imagined as a microscopic billiard ball following a perfectly defined classical path. Photons also produce interference and diffraction, behaviours that cannot be explained by ordinary pellets travelling through space. A photon is a quantum excitation of the electromagnetic field. It produces localized exchanges of energy and momentum when detected, but its behaviour between preparation and measurement is described through quantum amplitudes, rather than a simple hidden trajectory. Compton scattering remains important far beyond its historical role. In medical imaging, scattered photons affect image quality and the radiation dose received by patients. Some imaging systems also reconstruct the direction of incoming radiation from measured Compton events. Radiation detectors use the characteristic distribution of scattered electrons and photons to identify energetic radiation. Gamma-ray telescopes employ similar principles to study violent cosmic environments, including supernova remnants, pulsars, active galaxies, and bursts produced across enormous distances. Inside stars and hot astronomical plasmas, photons repeatedly scatter from electrons, exchanging energy and momentum as radiation moves through matter. Inverse Compton scattering occurs when energetic electrons transfer energy to lower energy photons, raising them into the X-ray or gamma-ray range. A beam of X-rays striking graphite had therefore revealed a principle operating throughout laboratories, hospitals, stars, and distant galaxies. Light could behave as a wave across space, yet arrive at matter through individual interactions carrying measurable energy and momentum. The classical distinction between radiation and particles had weakened further, replaced by a quantum description in which nature borrowed features from both while belonging completely to neither. Some of the most important experiments in quantum physics began with a surprisingly simple idea. Allow a beam of atoms to travel through empty space, place something in its path, and see how the beam changes. Otto Stern helped develop this molecular beam method during the early 20th century. A material was heated inside an oven until atoms or molecules escaped through a small opening. A series of narrow slits then shaped the emerging particles into a thin beam. The beam travelled through a vacuum, reducing the collisions that would otherwise blur its motion, before striking a collecting surface where its position could be measured. This technique gave physicists an unusually clean way to investigate individual properties of atoms. Instead of studying dense gases, liquids, or solids in which enormous numbers of particles continually collided, they could send a narrow stream through a controlled region and observe how an external field altered its path. In 1922, Otto Stern and Walter Gerlach used this method in Frankfurt to investigate the magnetic behaviour of silver atoms. Their apparatus was delicate, compact, and difficult to operate. Silver was heated until a beam of neutral atoms emerged from an oven. Those atoms passed through narrow openings and then entered a strongly non-uniform magnetic field. The use of neutral atoms was important. An electrically charged particle moving through a magnetic field experiences a force because of its charge and motion. A neutral silver atom avoids that ordinary deflection. Any change in its path could instead reveal an internal magnetic property. Atoms were expected to behave somewhat like tiny magnets. Moving electric charge can produce a magnetic moment, and the early atomic model suggested that the motion of electrons within an atom should give it a preferred magnetic direction. A uniform magnetic field can turn a magnetic object without necessarily pulling it toward one side. Stern and Gerlach therefore used a field that varied strongly across space. One pole of their magnet had a sharply pointed shape, producing a steep magnetic field gradient. An atom with one magnetic orientation would be pulled toward the stronger part of the field, while an atom oriented in the opposite direction would be deflected the other way. According to classical physics, the magnetic axes of atoms in the incoming beam should have pointed in every possible direction. Some would have been aligned strongly with the field, others would have opposed it. Many more would have occupied every intermediate angle. The deflection should therefore have formed a continuous spread on the collecting plate. A few atoms would move strongly upward, a few strongly downward, and the remainder would fill the space between them. The expected result was a broad smear. That was not what appeared. The silver atoms separated into two distinct traces. Instead of displaying a continuous range of magnetic deflections, the beam divided into two groups, leaving an empty region between them. For the measured component of the atom's magnetic moment, nature appeared to permit two outcomes and no intermediate ones. The result provided striking evidence for space quantization. A property associated with the atom's magnetic orientation could not take every value predicted by the classical picture. When measured along the direction selected by the apparatus, it appeared in discrete amounts. Stern and Gerlach initially interpreted the result within the Bohr-Sommerfeld model of the atom. In that older framework, electrons were imagined as following particular quantized orbits around the nucleus. The experiment seemed to show that these orbital motions could adopt only certain orientations relative to the magnetic field. The later explanation proved more subtle. The silver atom contains 47 electrons. Most of those electrons are arranged in filled shells whose magnetic contributions largely cancel. The atom's relevant magnetic behaviour comes mainly from its single outer electron. The two-way splitting is now understood through the intrinsic spin of that electron. Electron spin was introduced in 1925 by George Uhlenbeck and Samuel Goudsmit, building on ideas connected with Wolfgang Pauli's exclusion principle and his two-valued quantum degree of freedom. Spin resembles angular momentum in its mathematical behaviour, but it is not produced by an electron literally spinning like a small solid sphere. That image quickly runs into trouble. The electron has no confirmed internal surface that could rotate, and a classical spinning model would require impossible behaviour to reproduce the measured magnetic moment. Spin is instead an intrinsic quantum property. It belongs to the electron in the same fundamental sense that electric charge and mass belong to it. For an electron, a spin measurement along any chosen axis has two possible results. These are commonly described as spin up and spin down relative to that axis. The words up and down do not refer to permanent directions attached to the electron. They describe the two allowed results defined by the orientation of the measuring apparatus. This distinction becomes clearer when several Stern-Gerlach devices are considered in sequence. Suppose a first device is aligned vertically. It divides an incoming beam into two components. Selecting the upward component prepares atoms in a definite spin state relative to the vertical axis. If those atoms enter a second device with the same orientation, they all emerge through the same upward channel. Repeating the same measurement gives a predictable result. Now rotate the second device so that it measures along a horizontal axis. The previously prepared atoms divide into two beams again. A state that was definite vertically does not possess a definite horizontal spin result. The two horizontal outcomes appear with equal probability. The effect becomes stranger when one horizontal output is selected and sent through another vertically aligned device. The beam once again splits into both vertical outcomes. The intermediate horizontal measurement has removed the certainty created by the first vertical measurement. This is not merely the accidental jostling of atoms by a crude instrument. It reflects the structure of quantum measurements. Spin components along different axes are incompatible observables. A state can be definite with respect to one orientation, while remaining a superposition of the possible results associated with another. Measurement therefore does more than uncover a complete set of pre-existing classical directions. The apparatus defines which spin component is being tested. The interaction prepares a state associated with one of the permitted outcomes, while information about an incompatible component is no longer definite in the same way. The Stern-Gerlach experiment provided a concrete route into several of the deepest features of quantum mechanics. It revealed quantized measurement outcomes. It helped expose intrinsic spin. It demonstrated the importance of the chosen measurement direction. Sequences of similar devices illustrate superposition, state preparation, probability, and the disturbance involved in obtaining quantum information. Its influence now extends far beyond silver atoms crossing a magnet. Spin states are central to magnetic resonance imaging, nuclear magnetic resonance, atomic clocks, precision spectroscopy, particle beam experiments, and measurements of magnetic materials. They also provide one of the clearest physical models of a quantum bit. A quantum bit can be prepared in either of two basis states or in a superposition of both, just as a spin system can be described relative to two possible measurement outcomes. The original experiment was performed with a beam, a furnace, a vacuum chamber, and a carefully shaped magnet. Yet its result reached deep into the structure of matter. The atoms did not spread across every classically permitted path. They quietly chose between two distinct traces, revealing that even direction itself could be quantized when nature was asked the right question. The growing evidence that light could behave like a particle created an obvious and rather unsettling question. If something long understood as a wave could arrive in localized packets, might something long understood as a particle also behave like a wave? In 1924, the young French physicist Louis de Broglie proposed exactly that. De Broglie argued that wave-particle duality should not belong only to light. Matter itself, including electrons, atoms, and perhaps every moving object, should possess a wavelength related to its momentum. The relationship can be expressed in words. The wavelength associated with a particle equals Planck's constant divided by the particle's momentum. A particle with low momentum has a relatively long wavelength. A particle with high momentum has a shorter one. Because Planck's constant is so extraordinarily small, the wavelengths associated with ordinary objects are far too tiny to observe. A moving football has a matter wavelength so minuscule that no realistic experiment could reveal its interference. Electrons are much lighter. Their momenta can be small enough for the associated wavelength to become comparable with the spacing between atoms inside a crystal. At that scale, wave behaviour should become measurable. The proposal was difficult to accept because electrons appeared thoroughly particle-like. Joseph John Thomson had identified the electron through experiments with cathode rays, showing that it carried negative electric charge and possessed a measurable ratio of charge to mass. Robert Millikan later measured the electron's charge directly. Electrons could strike screens at particular locations, curve through electric and magnetic fields, and transfer energy and momentum in individual interactions. Nothing about this familiar behaviour suggested a wave spread across space. De Broglie was not claiming that an electron was secretly made from an ordinary material ripple. He was suggesting that the mathematical description of matter included a wavelength, just as the description of light included both wave behaviour and localized quantum exchanges. The idea initially had little direct experimental support. That changed through work at Bell Telephone Laboratories in the United States. Clinton Davison and Lester Germer were studying how electrons scattered from metal surfaces. Their apparatus produced a beam of electrons, accelerated it through a known electrical potential, and directed it onto a nickel target inside a vacuum chamber. A movable detector measured how many electrons emerged at different angles. The experiment was not originally designed as a grand test of matter waves. Its connection with de Broglie's proposal became clear only after a fortunate complication. Air accidentally entered the vacuum apparatus, oxidizing the nickel surface. To restore the target, the researchers heated it strongly. This treatment caused many small regions within the nickel to grow into larger, more orderly crystals. The repaired target was therefore better suited to diffraction than the original surface had been. Experimental equipment occasionally advances physics by breaking in just the right way. A crystal is not simply a uniform block of matter. Its atoms are arranged in a repeating structure, with regular spacings comparable to the wavelengths associated with accelerated electrons. Layers of atoms can therefore act like a three-dimensional diffraction grating. Diffraction is a characteristic wave phenomenon. When waves encounter regularly spaced structures, parts of the wave scatter from different locations. Those scattered contributions then overlap. When their peaks and troughs align, they reinforce one another through constructive interference. When a peak meets a trough, they cancel through destructive interference. The result is not a smooth distribution in every direction, but a pattern containing strong maxima and weak regions. This behaviour was already familiar from light passing through narrow openings and from X-rays scattered by crystals. William Henry Bragg and William Lawrence Bragg had shown how the angles of strong X-ray reflection could reveal the spacing between atomic planes inside a crystal. If electrons possessed de Broglie wavelengths, a nickel crystal should produce similar angular patterns. Davison and Germer varied the energy of the electron beam and measured the intensity of scattered electrons across different directions. In 1927, they reported a pronounced peak at an angle, an electron energy that matched the prediction for diffraction from the nickel crystal. The wavelength inferred from the diffraction pattern agreed closely with the value calculated using de Broglie's relation. This was not a vague resemblance. The electron momentum was determined by the accelerating voltage, allowing the predicted wavelength to be calculated independently. The crystal spacing and measured scattering angle then produced an experimental wavelength. The two values matched. A speculative extension of wave-particle duality had become a measured property of matter. At nearly the same time, George Paget Thomson performed an independent form of the experiment. He directed fast electrons through extremely thin metal films rather than scattering them from the surface of one crystal. The films contained many tiny crystals facing in different directions. As the electrons passed through, they were diffracted by the regularly arranged atoms. A photographic plate recorded a series of concentric rings. Those rings were exactly the kind of pattern expected when waves scatter from many randomly oriented crystals. Their diameters changed predictably as the electron momentum changed, again agreeing with de Broglie's wavelength. The historical contrast was difficult to miss. George Paget Thomson demonstrated the wave behaviour of electrons, while his father, Joseph John Thomson, had helped establish their particle character. Physics had managed to give the same family evidence for both sides of the electron's identity. Yet calling one experiment particle evidence and another wave evidence can still create the wrong picture. An electron is not switching between being a tiny ball and being a miniature water wave. Those are classical categories, and neither is complete. In quantum mechanics, the electron is described by a wave function. This wave function contains probability amplitudes associated with different possible outcomes. These amplitudes can spread, combine, and interfere. The probability of detecting the electron at a particular place is obtained from the wave function, but the detection itself occurs as one localized event. In the diffraction experiments, each electron eventually arrived at one location in the detector or photographic plate. No single electron appeared as a faint smear across the complete pattern. After many electrons had been recorded, however, their individual impact formed a distribution containing diffraction peaks and interference structure. The wave, therefore, does not represent a classical substance spread thinly through space. It describes the quantum possibilities governing where localized results can occur. Electron diffraction soon became much more than a foundational demonstration. Because electron wavelengths can be far shorter than visible light wavelengths, electrons can reveal much smaller structures. Visible light microscopes are limited by diffraction and cannot resolve details much smaller than a few hundred nanometers. Properly accelerated electrons can possess wavelengths thousands of times shorter, although the practical resolution of an electron microscope also depends on lenses, vibrations, sample preparation, and other engineering limits. Transmission electron microscopes pass electrons through very thin samples, while scanning electron microscopes examine surfaces by moving a focused beam across them. These instruments can reveal fine structures in cells, crystals, metals, semiconductor devices, and nanoscale materials. Electron diffraction also helps determine the arrangement of atoms inside solids. It supports research into alloys, superconductors, thin films, and semiconductor components. Modern electronics depends heavily on understanding crystal structures and the behaviour of electrons within them. The deeper lesson remains as remarkable as the technology. Matter, which had seemed to define the particle side of the old distinction, produced unmistakable wave patterns. Electrons carried charge, mass, energy, and momentum, yet they also diffracted and interfered according to a measurable wavelength. The wave was not hidden inside the electron as a mechanical vibration. It was part of the quantum description of what the electron could do. Nature had not merely blurred the boundary between waves and particles, it had revealed that the boundary belonged to classical language, not to the underlying world. Few experiments reveal the difference between classical and quantum physics more clearly than the double-slit. Its story began long before quantum mechanics. During the early 19th century, Thomas Young directed light toward a barrier containing two narrow openings. Beyond the barrier, the light formed alternating bright and dark bands rather than two simple illuminated patches. This was the pattern expected from waves. When water waves pass through two openings, each opening becomes the source of spreading ripples. Where the crests of the two waves meet, they reinforce one another, producing a stronger disturbance. Where a crest from one wave meets a trough from the other, they cancel. This combination of reinforcement and cancellation is called interference. Young's experiment provided strong evidence that light behaved as a wave. The bright bands resulted from constructive interference, while the dark bands came from destructive interference. At the time, this helped overturn the idea that light consisted only of ordinary particles travelling along straight paths. Quantum physics later returned to the same arrangement and made it considerably stranger. Instead of sending an intense beam of light through both openings, physicists could reduce the source until photons arrived individually. Similar experiments could be performed with electrons, neutrons, atoms, and eventually molecules containing dozens or even thousands of atoms. Whatever entered the apparatus, each detection appeared as one localized event. A photon activated one small region of a detector, an electron produced one spot on a screen. A molecule arrived at one measured position, rather than spreading itself visibly across the entire surface. At first, these isolated impacts appeared random. One particle landed here, another appeared somewhere else, and no clear order could be seen. As more detections accumulated, however, a pattern slowly emerged. The separate impacts formed alternating regions of high and low probability. A full interference pattern appeared, even when the particles had passed through the apparatus one at a time. This ruled out the simplest explanation that particles were colliding with one another and somehow organizing themselves into stripes. Each particle travelled through the apparatus without another particle beside it. Whatever produced the interference had to be present within the quantum description of each individual event. In 1961, Klaus Janssen performed an electron double-slit experiment that demonstrated clear interference from electrons passing through extremely narrow openings. Later experiments made the individual build-up of the pattern easier to observe. Akira Tonomura and his colleagues used an electron beam prism, an arrangement that separates and then recombines parts of an electron wave using electric fields rather than two ordinary physical slits. Electrons arrived at the detector one by one. The earlier spots appeared scattered and unstructured. After thousands of impacts, bright and dark fringes became unmistakable. The screen never recorded half an electron in one place, and the remaining half elsewhere. Every electron produced one complete localized detection, yet the overall distribution behaved as though something associated with each electron had explored both available alternatives and interfered with itself. Quantum mechanics describes that something with a wave function. The wave function assigns a probability amplitude to each possible result. These amplitudes are not ordinary probabilities. They include information about relative phase, which determines whether different alternatives reinforce or cancel one another. When there are two available paths, quantum mechanics assigns an amplitude associated with one path and another amplitude associated with the other. The amplitudes combine before the probability of a detection is calculated. Where the phases align, constructive interference makes detection more likely. Where they oppose one another, destructive interference reduces the probability, sometimes almost to zero. This distinction is essential. If ordinary probabilities were added directly, opening a second slit could only increase the chance of a particle reaching each region of the screen. In the actual experiment, opening the second path can make some locations less likely than they were with only one path available. The extra possibility can remove outcomes through interference. Classical probability does not normally behave that way. The pattern changes when the experiment is modified to reveal which path the particle followed. A detector might interact with the particle near one slit, or the two paths might become marked by different internal states, polarizations, or environmental effects. When reliable which path information exists, the interference fringes disappear. This does not require a person to sit beside the apparatus and consciously read the detector. The relevant change occurs through a physical interaction. The particle becomes correlated or entangled with the measuring device or the surrounding environment. If the state of the detector differs according to the path taken, the two alternatives are no longer fully indistinguishable. Information about the route has entered the wider physical world, even if nobody later examines it. The process is closely connected with decoherence. When a quantum system interacts with many uncontrolled environmental particles, information about its possible alternatives spreads into those surroundings. The relative phase relationships required for visible interference become inaccessible. A grain of dust, a stray photon, or a collision with a gas molecule can carry away path information. Large objects interact with their environments constantly, which is one reason obvious interference between everyday alternatives is so difficult to observe. It is tempting to say that measurement simply disturbs the particle and mechanically knocks it away from its original route. Physical disturbance can matter, but it is not the whole explanation. Carefully designed experiments can eliminate interference through path information even when the momentum transfer to the particle is extremely small. The deeper issue is distinguishability. Interference requires alternatives that remain coherent and physically indistinguishable. Once the alternatives become recorded in separate states of another system, the interference available in the original measurement is suppressed. This produces the central tension of the double-slit experiment. Every run ends with one definite result. The detector records a particle at one place, and not at several places simultaneously. Yet the probabilities governing those definite results cannot be reproduced by assigning the particle one ordinary classical path while ignoring the other. The successful mathematical description requires amplitudes associated with multiple possibilities. Different interpretations of quantum mechanics explain this in different ways. Some treat the wave function primarily as a tool for predicting measurement outcomes. Others regard it as a real physical structure. Still others introduce branching worlds, hidden trajectories, relational properties, or physical collapse processes. The experiment itself does not select one interpretation beyond all dispute. It does, however, establish the behaviour that every viable interpretation must explain. The double slit is sometimes presented as proof that human consciousness creates reality. The experiment shows no such thing. Detectors, atoms, photons, and environmental interactions can remove interference without a conscious observer being involved. What it demonstrates is both more precise and more profound. Quantum possibilities combine according to wave-like rules, while observations produce individual localized events. The relationship between those possibilities and the single outcome that eventually appears remains one of the deepest questions in physics. A simple barrier with two narrow paths therefore reveals the full unease of the quantum world. One particle arrives in one place, but the pattern formed over time remembers alternatives that no ordinary classical particle could have taken together. By the middle of the 1930s, quantum mechanics had already become one of the most successful theories ever created. Werner Heisenberg's matrix mechanics, Erwin Schrödinger's wave equation, Max Born's probability interpretation, and Paul Dirac's relativistic theory of the electron could explain atomic spectra, chemical bonding, and the behaviour of matter with remarkable accuracy. Paul Dirac's work was especially important because it brought quantum mechanics together with Albert Einstein's special theory of relativity. His equation described the electron's intrinsic spin naturally, predicted its magnetic properties, and even pointed toward the existence of antimatter before the positron was discovered experimentally by Carl Anderson. Yet serious problems appeared when physicists tried to describe interactions between charged particles and the electromagnetic field in complete quantum detail. Calculations often produced infinite answers. An electron interacting with its own field seemed to acquire infinite energy. Corrections to atomic states could also become mathematically unbounded. The theory was clearly revealing something real, but its mathematical machinery occasionally behaved as though it had wandered into a room and forgotten where the exits were. A particularly precise test came from the hydrogen atom. Hydrogen contains one electron bound to one proton. Its simplicity makes it an ideal system for comparing theory with experiment. According to the Dirac equation, two specific excited states of hydrogen should possess exactly the same energy. These states differed in the details of their orbital angular momentum, but the relativistic quantum theory predicted that their energies would coincide. In the language of spectroscopy, they were degenerate. If an experiment could detect even a tiny separation between them, it would show that the Dirac equation, powerful though it was, did not contain the complete description. In 1947, Willis Lamb and Robert Rutherford performed such a measurement at Columbia University. They used microwaves to induce transitions between closely related states of hydrogen. Rather than relying only on visible spectral lines, they examined the atom with radio frequency techniques developed partly through wartime advances in radar. The results showed that the two states did not have precisely the same energy. One lay slightly above the other. The difference was extremely small. Expressed as a frequency, it was a little over 1,000 million cycles per second, tiny compared with the overall frequencies associated with atomic energy. Yet the measurement was clear and repeatable. This separation became known as the Lamb shift. The effect was not a dramatic beam splitting across a screen or a bright interference pattern slowly appearing from individual particles. It was a subtle displacement in the energy structure of hydrogen. Nevertheless, that small difference exposed a missing piece in the theory. Soon after hearing about the result, Hans Bethe produced an approximate calculation while travelling by train. He showed that the shift could be understood by considering the interaction between the electron and the electromagnetic field, provided the divergent parts of the calculation were handled carefully. This approach became part of the wider development of renormalized quantum electrodynamics. Quantum electrodynamics is the quantum field theory of electrically charged particles and the electromagnetic field. It describes electrons, positrons, and photons, as well as the ways they exchange energy and momentum. Julian Schwinger, Richard Feynman, and Shinichiro Tomonaga developed powerful methods for obtaining finite testable predictions from the theory. Freeman Dyson later demonstrated the connection between Schwinger's formal approach, Tomonaga's work, and Feynman's more visual method using diagrams. Renormalization did not simply erase inconvenient infinities and hope nobody noticed. It reorganized the calculation around physical quantities that could actually be measured, such as the observed charge and mass of the electron. The unobservable bare quantities within the mathematical description were absorbed into these measured values, leaving finite corrections that experiments could test. The Lamb shift arises because the electron in hydrogen does not exist independently of the quantum electromagnetic field. Even in its lowest energy state, the electromagnetic field is not equivalent to classical emptiness. It retains quantum fluctuations. The electron continually interacts with this field, and those interactions slightly modify the energy associated with its atomic state. One useful description involves fluctuations in the electron's effective position. Another concerns the electron interacting with the field it generates. The full explanation includes effects known as electron self-energy and vacuum polarization. Different hydrogen states respond slightly differently to these interactions because their wave functions are distributed differently around the proton. The resulting energy corrections remove the exact degeneracy predicted by the simplest Dirac treatment. This does not mean that visible particles are constantly appearing from literal nothingness around the atom. Popular descriptions often speak of virtual particles briefly popping into existence, but that picture must be handled cautiously. Virtual particles are elements within particular calculation methods, especially perturbation theory and Feynman diagrams. They help organize the possible interactions contributing to a measurable result. They are not ordinary particles traveling freely through a detector, and they cannot be directly isolated in the same way as real photons or electrons. The measurable Lamb shift is real. The virtual particle story is one way of representing the mathematical contributions that produce it, not a microscopic film of hidden objects being observed directly. A related precision test appeared at almost the same time. The Dirac equation predicted a particular relationship between the electron's spin and its magnetic moment. In 1947, Polycarp Cush and Henry Foley measured the magnetic behaviour of electrons bound within atoms and found a small departure from the simplest prediction. The electron's magnetic moment was slightly larger than the Dirac theory alone allowed. Julian Schwinger calculated the leading correction using quantum electrodynamics. The correction depended on the fine structure constant, which measures the strength of electromagnetic interaction. His result agreed with the experimental deviation and became one of the early triumphs of the renormalized theory. Later calculations included increasingly elaborate contributions, while experiments measured the electron magnetic moment with extraordinary precision. Today, the comparison between theory and experiment reaches agreement across many decimal places, making it one of the strictest tests of any physical theory. These experiments demonstrated that scientific revolutions do not always arrive through large and obvious failures. Sometimes the crucial evidence is a tiny difference between two nearly identical energy levels or a minute correction to a magnetic property. The Lamb shift forced physicists to take the quantum electromagnetic field seriously. It showed that the apparent emptiness surrounding an atom participates in the atom's measurable behaviour. Empty space in quantum field theory is not a region where every physical structure has vanished. It is the lowest energy state of fields that remain present throughout space. Those fields can influence atomic energies, magnetic moments, and the outcomes of precision experiments. A faint microwave transition in hydrogen therefore helped rebuild the foundations of quantum physics. The experiment revealed that even when an atom appears isolated, it is never entirely alone. It remains embedded within quantum fields whose quiet activity leaves a measurable signature on matter. Quantum behaviour is often associated with individual atoms, electrons, and photons, all safely hidden at scales far below ordinary sight. Superconductivity revealed that quantum rules could also organise an entire piece of material, producing effects large enough to measure with wires, magnets, and electrical circuits. The discovery began with the attempt to reach extremely low temperatures. In 1908, the Dutch physicist Heike Kamerlingh-Onnes successfully liquefied helium at his laboratory in Leiden. Liquid helium allowed matter to be cooled to only a few degrees above absolute zero, the lowest possible temperature. Onnes then investigated how metals conducted electricity under these unfamiliar conditions. Ordinary metals generally become better conductors as they cool because their atoms vibrate less vigorously, reducing the scattering experienced by moving electrons. In 1911, Onnes cooled mercury to approximately 4.2 degrees above absolute zero. Its electrical resistance did not merely decline gradually, it suddenly fell below the level his equipment could measure. Onnes had discovered superconductivity. An extremely good ordinary conductor still possesses some electrical resistance. Electrons moving through it scatter from vibrating atoms, impurities, and imperfections in the material. Electrical energy is gradually converted into heat, which is why ordinary wires warm when they carry large currents. A superconductor behaves differently. Below a characteristic critical temperature, it can carry an electrical current without the usual dissipative resistance. Once established in a closed superconducting ring, a current can persist for extraordinarily long periods without a battery continually replacing lost energy. This does not mean that superconductors ignore every physical limit. Excessive temperature, current, or magnetic field can destroy the superconducting state. Within the correct range, however, electrical resistance effectively disappears. For several decades, physicists wondered whether superconductivity was simply perfect conductivity. An important experiment showed that the phenomenon was more fundamental. In 1933, Walter Meissner and Robert Oxenfeld cooled superconducting materials while magnetic fields passed through them. They found that the magnetic field was expelled from the interior as the material entered the superconducting state. This became known as the Meissner effect. A hypothetical perfect conductor would merely preserve whatever magnetic field had already existed inside it. A superconductor actively rearranges electrical currents near its surface so that the magnetic field is largely excluded from its interior. Superconductivity is therefore a distinct thermodynamic phase of matter, not simply ordinary conductivity improved to an impressive degree. The material enters a new collective state with its own measurable properties. The microscopic explanation arrived in 1957 through the work of John Bardeen, Leon Cooper, and Robert Schrieffer. Their theory became known as the Bardeen-Cooper-Schrieffer theory. Electrons normally repel one another because they carry the same negative electric charge. Inside certain cold crystalline materials, however, an electron moving through the lattice can slightly distort the positions of the positively charged atomic ions. That distortion can influence another electron. Under suitable conditions, the interaction produces an effective attraction between electrons, mediated by vibrations of the crystal lattice known as phonons. The attraction is weak, yet at sufficiently low temperatures it allows electrons near the material's Fermi surface to form correlated pairs. These are called Cooper pairs. The two electrons in a conventional Cooper pair possess opposite momenta and opposite spins. Together, they behave collectively in a way that differs from individual electrons. An enormous number of Cooper pairs can occupy a coherent quantum state described by a shared phase. This coherence is the heart of superconductivity. In an ordinary conductor, electrons scatter independently and lose organized motion to the surrounding material. In a superconductor, the paired electrons belong to one coordinated quantum state. Disturbing a single pair generally requires enough energy to overcome a protective energy gap. At low temperature, ordinary vibrations often cannot provide that energy. The superconducting current can therefore move without the usual resistance. The quantum state may extend across a wire, ring, or manufactured circuit large enough to see and hold. Quantum phase, normally introduced through microscopic wave functions, becomes a physical property influencing the behaviour of a macroscopic object. An especially clear demonstration appeared through magnetic flux quantization. In 1961, Bascom Deaver and William Fairbank observed that magnetic flux trapped inside a superconducting cylinder did not take arbitrary values. Robert Dahl and Martin Neubauer independently found the same behaviour using a superconducting ring. The trapped magnetic flux appeared only in discrete units. The size of each unit is determined by Planck's constant and the charge of a Cooper pair. One magnetic flux quantum equals Planck's constant divided by twice the elementary electric charge. The factor of 2 reflects the pairing of electrons. Magnetic flux through the superconducting loop was therefore revealing both quantization and the charge carried by the coherent pairs. Soon afterward, another remarkable prediction connected superconductivity with quantum tunneling. Quantum tunneling allows a system to cross a barrier even when classical physics says it lacks enough energy to pass over it. In 1962, Brian Josephson considered two superconductors separated by an extremely thin insulating layer. He predicted that Cooper pairs could tunnel through the barrier while preserving their quantum coherence. When there is no voltage across the junction, a steady supercurrent can flow. Its size depends on the difference between the quantum phases on the two sides. This is known as the Dirac-Josephson effect. When a constant voltage is applied, the phase difference changes steadily, and the current oscillates at a precisely determined frequency. This is called the alternating Josephson effect. The relationship between voltage and oscillation frequency is so exact that Josephson junctions became important tools for establishing electrical measurement standards. Philip Anderson and John Rowell soon produced early experimental evidence for Josephson tunneling. The effect helped transform superconductors from unusual cold materials into controllable quantum devices. One of the most sensitive devices built from Josephson junctions is the superconducting quantum interference device. It uses a superconducting loop interrupted by one or more thin junctions. Quantum amplitudes associated with currents travelling around the loop interfere with one another. Small changes in magnetic flux alter their relative phase and produce measurable changes in electrical current or voltage. These instruments can detect extraordinarily weak magnetic fields. They are used in geology, materials research, medical measurements, and experiments searching for subtle physical signals. Superconducting circuits also provide one of the leading platforms for quantum computing. Josephson junctions give carefully designed circuits discrete energy levels, allowing them to behave like artificial atoms. The lowest levels can represent the two logical states of a quantum bit. Microwave pulses prepare superpositions, control phase, produce entanglement, and read out the resulting state. These circuits are much larger than natural atoms, yet they follow recognizably quantum rules. Their behaviour depends on tunneling, interference, quantized energy, and coherent phase across manufactured components. Superconductivity therefore brought quantum physics into the visible world. A piece of metal could expel a magnetic field, preserve a current, trap flux in discrete units, and allow paired electrons to tunnel coherently across a barrier. The quantum state was no longer confined to one particle in one tiny region. It could stretch across an entire circuit, quietly coordinating the motion of vast numbers of electrons as though the material had learned to behave as one. Quantum mechanics had survived every major experimental test placed before it, yet some of its most successful creators remained deeply divided over what the theory actually described. Niels Bohr argued that quantum mechanics provided a complete framework for predicting the outcomes of experiments. Physical properties such as position, momentum, or spin could not always be treated as possessing definite values independently of the experimental arrangement used to measure them. The conditions of measurement were not a minor practical detail. They helped define which physical question was being asked. Albert Einstein was not satisfied with this view. He accepted that quantum mechanics produced remarkably accurate predictions, but he doubted that its probabilities represented the deepest level of physical reality. He suspected that the theory was incomplete and that a more detailed description might restore definite properties and ordinary causal explanations beneath the observed randomness. Einstein's concern was not simply that quantum mechanics was strange. He had helped create the quantum revolution himself through his explanation of the photoelectric effect. His objection was more precise. A physical theory should, in his view, describe what exists rather than merely provide probabilities for what an experimenter may observe. The disagreement became especially sharp when quantum mechanics was applied to systems that had interacted and then moved far apart. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published an argument intended to show that the quantum description could not be complete. Their reasoning involved two particles prepared in a shared state, with strongly correlated properties. The original version focused on position and momentum. The particles were arranged so that measuring the position of one would allow the position of the other to be predicted, while measuring the momentum of the first would allow the momentum of the second to be inferred. Once the particles were separated, the experimenter could choose which property to measure on the first particle. If measuring the first particle allowed the corresponding property of the distant particle, to be predicted with certainty, and if no physical influence could travel instantly between them, Einstein and his colleagues argued that the distant particle must already possess that property. Yet quantum mechanics did not assign definite values for both position and momentum at the same time. Einstein, Podolsky, and Rosen concluded that the wave function left out elements of physical reality. Their argument relied on locality, the idea that a physical action performed in one region should not instantly alter the real state of a distant object. This was closely connected with special relativity, which prevents signals and causal influences from travelling faster than light. The quantum state at the centre of the argument is now described as entangled. Entanglement occurs when the state of a combined system cannot be divided into separate, independent quantum states for its parts. The system must be described as a whole, even when its components are widely separated. This does not simply mean that the particles possess ordinary matching properties. A pair of gloves placed into different boxes would also display a correlation. Opening one box and finding a left glove would immediately reveal that the other box contained the right glove. Nothing mysterious would occur because each glove possessed its identity before either box was opened. Entangled particles behave differently. Quantum mechanics does not generally describe each particle as carrying a complete set of definite answers for every possible measurement. Instead, it assigns a state to the pair and predicts correlations between outcomes for measurements made along different chosen directions. Erwin Schrödinger introduced the term entanglement shortly after the Einstein-Podolsky-Rosen paper appeared. He regarded it not as a minor curiosity, but as the defining feature that separated quantum mechanics from classical physics. Once systems interact, their individual descriptions can become inseparable, even after the systems move apart. The original position and momentum argument was conceptually powerful but difficult to translate into a practical laboratory test. David Bohm later reformulated the problem using pairs of particles with correlated spin. Imagine two spin-carrying particles produced in a combined state, with total spin equal to 0. When the same spin direction is measured on both particles, the outcomes are always opposite. If one result is spin up, the other is spin down. A classical explanation seems tempting. Perhaps each particle leaves the source carrying hidden instructions that determine how it will respond to every possible detector orientation. The experiment merely reveals an answer that was present all along. This kind of explanation belongs to a broad family of local hidden variable theories. The hidden variables would provide the missing information absent from the ordinary quantum state. Locality would ensure that changing the measurement setting on one side could not instantly affect the distant particle. For many years, the difference between this picture and ordinary quantum mechanics appeared to be philosophical. Both seemed capable of reproducing the familiar opposite outcomes when the two detectors were aligned. The problem became experimentally testable through the work of John Stuart Bell. In 1964, Bell proved that any theory satisfying a particular combination of local hidden variable assumptions must place limits on the strength of correlations observed across many measurements. Quantum mechanics predicted correlations that could exceed those limits. The statistical boundary is known as a Bell inequality. The essential idea can be understood without following the full mathematics. Suppose each particle carries predetermined answers for several possible measurement directions. The experimenters independently choose which direction to test on each side. Because the particles cannot know the distant choice through any faster-than-light influence, their hidden instructions must produce a particular range of possible statistical relationships. Bell showed that these relationships cannot be arbitrarily strong. They must obey a numerical constraint. Quantum mechanics predicts that entangled particles can violate that constraint for carefully selected measurement directions. The results remain individually random, but the correlations between distant outcomes are stronger than any local hidden instruction system of the tested kind can reproduce. This transformed a disagreement about completeness into an experimental question. Physicists could create entangled pairs, choose detector settings, record many outcomes, and compare the measured correlations with the Bell limit. Bell's reasoning depends on clearly stated assumptions. Locality means that an outcome on one side is not directly influenced by the measurement choice made at a distant location during the experiment. The measurement settings must be chosen independently of the hidden variables carried by the particles. The outcomes must also be describable within the proposed hidden variable framework. Experiments can test combinations of these assumptions, although no finite experiment can eliminate every imaginable philosophical escape route. Some alternatives abandon locality, others question the independence of measurement choices, introduce retrocausal influences, or reject the idea that every outcome was uniquely determined in advance. Bell's theorem therefore does not prove that reality itself is unreal, nor does it eliminate every possible hidden variable theory. David Bohm's own hidden variable interpretation, for example, reproduces quantum predictions by being explicitly non-local. The precise result is that the correlations predicted by quantum mechanics cannot be explained by the broad class of local hidden variable models constrained by Bell inequalities. Entanglement also does not allow messages to travel faster than light. An observer measuring one particle sees a random sequence of results. No choice made at the distant detector can be identified from those local results alone. The unusual pattern becomes visible only when the two sets of data are later brought together and compared through ordinary communication. Einstein hoped that deeper variables would restore a more familiar form of locality and definite properties. Bell showed that this hope made predictions that could differ from quantum mechanics. A question that had seemed to belong entirely to interpretation had quietly entered the laboratory. The meaning of quantum theory was no longer separated from experiment. Nature itself could now be asked whether distant quantum correlations were merely the result of hidden local instructions, or whether the classical idea of independently existing objects had reached another of its limits. John Stuart Bell had transformed a philosophical disagreement into a numerical test, but his original theorem was not yet a ready-made laboratory instruction manual. Real experiments involved imperfect sources, inefficient detectors, limited measurement choices, and particles that frequently failed to arrive where they were expected. In 1969, John Clauser, Michael Horn, Abner Shimony, and Richard Holt reformulated Bell's reasoning into a version suitable for experiments using correlated photons. The result became known as the Clauser-Horn-Shimony-Holt inequality. Their approach compared correlations measured with several different settings of two distant polarization analyzers. Each analyzer could be rotated to test a different orientation. A photon reaching the apparatus would either pass through or be blocked, producing one of two possible outcomes. A local hidden variable model could imagine that every photon left the source carrying a private set of instructions. Those instructions would determine how it responded to each possible analyzer setting. Because the measurement on one side could not instantly influence the distant photon, the resulting correlations had to remain within a definite statistical limit. Quantum mechanics predicted that carefully prepared entangled photons could exceed that limit. The challenge was to create suitable photon pairs and measure enough of them to distinguish a genuine violation from ordinary statistical fluctuation. In 1972, Stuart Friedman and John Clauser performed one of the first decisive Bell tests at the University of California, Berkeley. Their source used excited calcium atoms. As each atom returned toward a lower energy state through a sequence of transitions, it emitted two photons with correlated polarizations. The photons travelled in opposite directions towards separate polarization analyzers and detectors. Friedman and Clauser rotated the analyzers through different combinations of angles, counted the coincident detections, and compared the observed correlations with the Bell limit. Their results agreed with quantum mechanics and violated the tested local hidden variable inequality. The experiment was historically important, but it was not perfect. Bell tests are difficult precisely because local explanations can exploit weaknesses in an experimental design. One major problem was detector efficiency. Early photon detectors registered only a small fraction of the particles produced by the source. Most photons were lost, absorbed, or simply failed to trigger a detector. The analysis therefore relied on a fair sampling assumption. It assumed that the detected photon pairs represented the complete collection fairly. If the missing photons behaved differently from the detected ones in a carefully coordinated way, a local hidden variable model might imitate the observed violation. This became known as the detection loophole. Another concern involved distance and timing. If the two measuring stations were too close together, or if their settings remained fixed for too long, information could in principle travel from one side to the other at or below the speed of light before the measurements were completed. A local explanation might then claim that the devices were communicating through some ordinary physical influence, rather than revealing genuinely non-local quantum correlations. This became known as the locality loophole. During the early 1980s, Alain Aspect and his colleagues at the Institute of Optics in Orsay, France, carried out a celebrated series of improved Bell tests. The researchers included Philippe Grangier, Gérard Roget, and Jean Dalibard. Like Friedman and Clauser, the Orsay group used photons emitted through an atomic cascade. Their apparatus produced stronger correlations, improved control over the measurement geometry, and reduced several experimental uncertainties. The most influential version introduced rapidly changing analyzer settings. Rather than leaving each analyzer fixed while the photons travelled, the experiment switched between alternative measurement orientations while the particles were already in flight. The switching was performed quickly enough to make ordinary communication between the two sides increasingly implausible as an explanation for the measured correlations. The timing was crucial. Light itself travels almost 300,000 kilometers each second, so even a separation of several meters allows only a few tens of billionths of a second before a signal could cross from one station to the other. The analyzers therefore had to change on extremely short timescales. Aspect's experiments again produced violations consistent with quantum mechanics. They did not close every loophole simultaneously. The detectors still missed many photons, and the setting choices were not generated in the fully independent and unpredictable manner used by later experiments. Even so, the work made the conflict with local hidden variable theories much harder to dismiss. The word loophole can make these issues sound like convenient philosophical evasions. In practice, each loophole corresponds to a precise experimental limitation. The locality loophole asks whether one measurement could have been influenced by information from the distant setting or outcome. The detection loophole asks whether the observed particles formed an unbiased sample of the particles that were actually produced. A further concern, often called the freedom of choice or measurement independence assumption, asks whether the selection of detector settings could somehow be correlated with the hidden variables emitted by the source. No experiment can defeat every logically imaginable conspiracy involving the entire history of the universe. It can, however, arrange events so that ordinary local explanations become increasingly restricted and unnatural. For several decades, different Bell experiments closed different loopholes. Experiments using trapped ions or other material systems achieved very high detection efficiency, but kept the particles close together, leaving the locality loophole open. Photon experiments separated their measurement stations widely but continued to lose too many particles. Gradual improvements changed the situation. Brighter and more stable entangled photon sources became available. Superconducting detectors achieved far higher efficiencies than earlier devices. Electronics could choose analyzer settings within billionths of a second. Atomic clocks and precision timing systems allowed distant events to be compared accurately. Solid-state quantum systems could preserve and measure entangled states with increasing reliability. These advances came together in 2015. A team led by Bas Henson at Delft University of Technology performed a Bell test using electron spins associated with nitrogen vacancy centers in diamond. The two main laboratories were separated by roughly 1.3 kilometers. Each electron spin became entangled with a photon. The photons traveled toward an intermediate station, where a successful joint detection event announced that the distant electron spins had become entangled with one another. This method is known as event-ready entanglement. Only trials in which the central station successfully established the connection were included, reducing the danger that undetected events could be selected unfairly. The researchers then chose measurement settings independently at the distant stations and completed the spin measurements quickly enough that neither side could receive a light-speed signal, revealing the other side's choice or result. The Delft experiment closed the principal locality and detection loopholes within the same test. The number of successful trials was relatively modest, but the measured violation was inconsistent with the tested local hidden variable models. During the same year, independent groups led by Marisa Justina in Vienna and Lyndon Shalm at the United States National Institute of Standards and Technology reported loophole-resistant Bell tests using entangled photons. These experiments benefited from highly efficient superconducting detectors, fast random setting choices, carefully separated measurement stations, and improved sources capable of producing entangled photon pairs reliably. The different approaches complemented one another. The Delft experiment used distant solid-state spins connected through photons. The Vienna and National Institute of Standards and Technology experiments relied more directly on photonic entanglement and extremely efficient optical detection. Together, they marked the arrival of Bell tests that simultaneously addressed the major experimental weaknesses that had remained since the 1970s. The conclusion is precise. Nature violates Bell inequalities. The observed correlations cannot be explained by local hidden variable models satisfying the assumptions tested by these experiments. This does not mean that a usable signal travels instantly between the particles. Each observer still sees an unpredictable sequence of individual outcomes. One side cannot control its results to send a message to the other. The correlation appears only after the two records are brought together and compared through ordinary communication, which remains limited by the speed of light. Bell violations therefore reveal non-local correlations without permitting faster-than-light signaling. Quantum mechanics preserves the causal communication limit of special relativity, even while refusing to describe distant systems as entirely independent objects carrying complete local instructions. Entanglement has since moved beyond tests of quantum foundations. It is now treated as a physical resource. Entangled systems support methods of quantum cryptography whose security can be connected to measurable violations of Bell inequalities. They can link nodes in experimental quantum networks, improve certain precision measurements, and distribute quantum information between distant devices. Quantum computers also rely on controlled entanglement to create correlations that cannot be reproduced by treating every quantum bit independently. What began as an argument between Albert Einstein and Niels Bohr therefore became an experimental program lasting more than half a century. Each generation tightened the test, improved the detectors, increased the distance, shortened the timing, and removed another possible local explanation. The resulting evidence does not make quantum mechanics less strange. It makes the strangeness measurable. Entangled particles do not merely behave as though they once agreed on matching answers. Their correlations exceed the limits available to systems carrying ordinary local instructions, revealing that the quantum world cannot be divided as cleanly into separate pieces as classical physics once assumed. The double-slit experiment had shown that quantum systems can display either interference or path information, depending on how the experiment is arranged. Niels Bohr described this relationship through the principle of complementarity. Complementarity does not mean that a particle secretly behaves as a wave at one moment and then changes into a classical particle at another. It means that different experimental arrangements reveal different aspects of a quantum system, and those aspects cannot always be displayed together within the same set of observations. An interference experiment preserves the coherence between alternative paths. The alternatives remain physically indistinguishable, allowing their probability amplitudes to combine. A path measurement does the opposite. It establishes information that can distinguish one route from the other, and the visible interference pattern disappears. The apparatus therefore matters. It determines which physical information can become available. John Archibald Wheeler pushed this principle into more unsettling territory with his delayed choice thought experiment. Wheeler imagined allowing a photon to enter an interferometer before deciding how the apparatus would finally measure it. An interferometer divides light into separate paths and later directs those paths toward detectors. Beam splitters perform the crucial work. A first beam splitter creates two possible routes. A second beam splitter can recombine them, allowing their quantum amplitudes to interfere. When the paths are recombined coherently, the detector statistics reveal interference. Under ideal conditions, constructive interference can direct nearly every photon toward one output, while destructive interference suppresses detections at the other. If the second beam splitter is removed, the paths remain separate. The detectors can then provide information about which route the photon followed through the apparatus. Wheeler asked whether the choice to insert or remove the final beam splitter could be delayed until after the photon had already passed the first one. In ordinary classical language, the photon should already have decided whether it travelled through one path like a particle, or explored both alternatives like a wave. Quantum mechanics does not require that simple history. Experimental versions of delayed choice have used photons, interferometers, rapidly controlled beam splitters, and measurement settings selected only after the quantum system entered the apparatus. The observed results agree with quantum theory. When the paths are recombined, interference appears. When they remain distinguishable, path information becomes available. The later choice does not force the photon to go backwards and alter an earlier decision. Rather, the experiment shows that quantum mechanics does not assign the photon one complete classical story, independent of the eventual measurement arrangement. The situation became even more intricate through the quantum eraser proposed by Marlon Scully and Kai Druhl. In a quantum eraser experiment, the possible paths become marked so that they can, in principle, be distinguished. The marking may be carried by another quantum property, or by a second particle entangled with the first. Once reliable path information exists, interference disappears from the ordinary detection pattern. Yet, if the path markers are measured in a different basis, one that does not reveal which route was taken, interference can reappear within carefully selected correlations. The information is not physically deleted from the past. The word eraser refers to arranging the final measurement so that the selected data no longer distinguish between the alternatives. A well-known delayed choice quantum eraser experiment was published in 2000 by Yoonho Kim, Rong Yu, Sergei Kulik, Yanhua Shi, and Marlon Scully. The experiment produced pairs of entangled photons. One photon, often called the signal photon, travelled toward a movable detector. Its entangled partner, often called the idler photon, entered a more complicated arrangement of beam splitters and detectors. The idler could be detected in ways that preserved which path information, or in ways that erased the distinction between the paths. Some idler detectors were associated with an identifiable route. Others received quantum amplitudes from both possible routes, and therefore did not reveal which one had occurred. The signal photon could be detected before the idler photon reached its own detector. This timing creates the delayed choice aspect, and has encouraged many dramatic claims about the future changing the past. The actual results are subtler. When all signal detections are examined together, they form no visible interference pattern. They appear as a broad, unstructured distribution. Nothing in this local record reveals which type of idler measurement will occur. The correlations become visible only when the signal detections are sorted according to the detector that later recorded the corresponding idler photon. One selected subset produces an interference pattern. Another produces a complementary pattern, sometimes called an anti-interference pattern. Where one subset contains a bright fringe, the other tends to contain a dark fringe. When these complementary subsets are added together, their fringes cancel. The combined signal data therefore remain smooth and show no usable interference. This cancellation is essential. An observer watching only the signal detector cannot determine whether path information was preserved or erased elsewhere. The earlier detections do not change when the later measurements occur and no recognizable message appears in them. Only after the signal and idler records are brought together through ordinary communication can the experimenters identify matching photon pairs and sort the data into the relevant subsets. There is therefore no backwards in time signaling, no information can be sent into the past, and no observer can use the experiment to learn a future choice before that choice is communicated normally. The ordering of the detections also does not change the joint quantum predictions. Quantum mechanics describes the correlated system as a whole. The pattern lies in the relationship between the two records, not in one detector receiving a mysterious instruction from the future. Popular explanations sometimes suggest that the later measurement forces the earlier photon to rewrite, whether it travelled through one path or both. This assumes that the photon must possess a single classical root before the complete experiment is considered. The experiments do not support that assumption. They show instead that path descriptions, interference, and correlations depend on which information the physical arrangement makes distinguishable. No conscious observer is required. Detectors can operate unattended, and the recorded outcomes remain the same whether anyone examines them immediately, much later, or not at all. Measurement refers to a physical interaction capable of storing information, not to human awareness. Delayed choice and quantum eraser experiments therefore do not demonstrate that the present alters an already settled past. They demonstrate that quantum phenomena cannot always be divided into a classical sequence in which every property existed definitely before it was measured. Interference depends on coherence between indistinguishable alternatives. Path information depends on correlations that distinguish those alternatives. Entanglement can distribute that information across separate particles, while the chosen measurement basis determines how the correlations become visible. The mystery does not come from time running backwards. It comes from the deeper fact that quantum mechanics describes possibilities and relationships that resist being compressed into one ordinary history. The photon is detected at one place. The experimental records remain consistent. Causes cannot be used to send messages into their own past. Yet the complete pattern still depends on how information is created, preserved, erased, and compared. Quantum reality remains orderly, but it is an order built around measurement context rather than the familiar assumption that every event carries one fully defined classical story from beginning to end. The quantum Zeno effect takes its name from a much older puzzle about motion. Zeno of Elea, an ancient Greek philosopher, imagined dividing a journey into an endless sequence of smaller distances. Before reaching a destination, a traveller must first cross half the distance. Before crossing that half, the traveller must cross half of it again, and the process can be repeated without end. Zeno used this reasoning to question how motion could ever be completed. Modern mathematics resolves the apparent paradox by showing that infinitely many shrinking intervals can add up to a finite distance and a finite time. The quantum Zeno effect is not a direct solution to Zeno's ancient puzzle, but it borrows the same general image. A process that would normally advance can sometimes be slowed, constrained, or almost frozen by checking it frequently enough. In 1977, Baidyanath Misra and George Sudarshan analysed the time evolution of unstable quantum systems. They showed that, under appropriate conditions, an extremely rapid sequence of measurements could inhibit a transition that would otherwise occur naturally. An excited atom, for example, may eventually decay into a lower energy state and emit a photon. A quantum system prepared in one state may also evolve gradually into a superposition containing another possible state. If nothing interferes with this evolution, the probability of finding the system in its original condition generally decreases with time. During a very short initial interval, however, this probability does not fall in the simple exponential manner associated with ordinary radioactive decay. Instead, the chance of leaving the original state begins quadratically with time. This small detail creates the possibility of the quantum Zeno effect. Suppose the system is repeatedly tested to determine whether it has changed. If each test finds it in the original state, the state is effectively prepared there again. When the measurements are performed sufficiently frequently, the system repeatedly begins its evolution from nearly the same starting point. The transition can therefore be strongly suppressed. This is sometimes summarized by saying that a watched quantum system does not change. The phrase is memorable, but it can also be misleading. No human being needs to stand beside the apparatus and watch with unusual determination. What matters is repeated physical interaction capable of distinguishing whether the transition has occurred. One influential demonstration was reported in 1990 by Wayne Itano, Daniel Heinzen, John Bollinger, and David Wineland at the United States National Institute of Standards and Technology. The researchers used thousands of beryllium ions confined by electromagnetic fields. The ions possessed internal quantum states that could be controlled using precisely tuned electromagnetic radiation. A sequence of pulses was arranged to transfer population from one state toward another. During this transition, the researchers applied additional pulses that repeatedly tested or effectively interrupted the evolving state. As the number of these intervening interactions increased, the transfer between the two states became progressively weaker. The ions remained closer to their initial state than they would have without the repeated pulses. This behaviour matched the suppression associated with the quantum Zeno effect. The interpretation of the experiment produced valuable scientific discussion. Some physicists argued that the result could be understood through ordinary coherent dynamics involving the applied fields, without describing every pulse as a separate collapse of the wave function. This does not make the effect less quantum mechanical. It clarifies that measurement is itself a physical coupling. A system can be constrained by repeated projective measurements, by continuous observation, or by strong interactions that continually distinguish different states. The essential mechanism is not consciousness. It is the way physical coupling alters quantum evolution. There is also an opposite possibility known as the anti-Zeno effect. Under certain conditions, repeated interactions can accelerate a transition rather than suppress it. The result depends on the timing of the measurements, the energy structure of the system, and the way it couples to its surroundings. A carefully chosen sequence may interrupt the natural evolution in a way that holds the system back. A different sequence may increase the system's access to states into which it can decay. The environment can therefore act like an observer in a precise physical sense. Collisions, stray electromagnetic fields, and surrounding particles can become entangled with the system and carry away information about its state. Depending on the form of that interaction, evolution may be slowed, redirected, or hastened. This replaces the vague idea of watching with a more useful description. Quantum measurement is an interaction through which information becomes physically recorded. A related attempt to examine quantum systems more gently appeared through the theory of weak measurement. In the late 1980s, Yakir Aharonov, David Albert, and Lev Vaidman proposed measurements designed to couple only faintly to a quantum system. An ordinary strong measurement normally produces one of the allowed outcomes clearly, while significantly altering the state. A weak measurement disturbs the system much less, but the information supplied by any individual trial is correspondingly vague. Noel Ritchie, James Story, and Randall Hewlett performed an early experimental demonstration using the polarization of light. Their measurements explored a quantity called a weak value, obtained by combining weak interaction with carefully chosen initial and final quantum states. A weak value can sometimes lie outside the ordinary range of possible results from a strong measurement. This does not mean that a single particle secretly possessed an impossible classical property. The unusual value emerges from statistics gathered across many similarly prepared trials and from the conditioning imposed by the final selection. The trade-off is unavoidable. A weak interaction preserves more of the original quantum state, but it provides very little reliable information on its own. Many repetitions are needed before a meaningful pattern emerges from the noise. Strong and weak measurements therefore reveal different balances between information and disturbance. Repeated strong interactions can inhibit evolution through the quantum Zeno effect. Gentle interactions can probe statistical features while reducing the effect of each individual measurement. In both cases, observation is not passive access to a fully formed classical reality. The apparatus becomes part of the physical process. It interacts, entangles, records and changes which future developments remain available. The quantum Zeno effect does not show that attention alone can freeze the world. It shows something more grounded and more useful. Asking a quantum system the same physical question again and again can alter the rate at which its answer changes. At the smallest scales, even watching has a cost because watching is something matter must physically do. For much of the early history of quantum physics, experiments reveal the behaviour of enormous collections of particles. A beam might contain countless electrons. A gas sample might hold billions upon billions of atoms. The results could be measured with great precision, but they usually represented an average across an immense ensemble. Over time, experimental techniques became sensitive enough to isolate individual quantum systems. Physicists could confine a single atom or ion, hold it nearly motionless, manipulate its internal state, and watch its behaviour through the light it emitted. This transformation depended heavily on the development of ion traps. An ion is an atom or molecule carrying a net electric charge because it has gained or lost one or more electrons. That charge makes it possible to control the ion using electric and magnetic fields. Wolfgang Paul developed an important form of electromagnetic confinement known as the Paul trap. A static electric field cannot hold a charged particle stably in every direction at once, but a rapidly changing electric field can create an effective region of confinement. The ion continually moves within the field, yet remains trapped near the centre rather than escaping. Another approach, refined by Hans Dehmelt, combined electric and magnetic fields in what became known as a penning trap. The magnetic field bends the motion of the charged particle, while an electric field prevents it from drifting away along the magnetic axis. These devices allowed ions and other charged particles to remain isolated for exceptionally long periods. Instead of racing through an apparatus in a fraction of a second, a particle could be held in one region and studied repeatedly. The surrounding chamber had to be evacuated carefully. Even a single collision with a stray gas molecule could disturb the trapped ion or knock it out of the trap. The resulting environment was not perfectly empty, but it contained vastly fewer particles than ordinary air. Confinement alone was not enough. A trapped ion still moved, carrying thermal energy that blurred precision measurements. Physicists therefore developed methods for cooling atomic motion with laser light. Laser cooling may sound contradictory, since shining light on something usually adds energy. The method works by tuning the laser slightly below a frequency that the ion absorbs most strongly. An ion moving toward the beam sees the light shifted upward in frequency by the Doppler effect and is more likely to absorb a photon. The absorbed photon delivers momentum opposite to the ion's motion, slowing it slightly. The ion later emits another photon in a nearly random direction. Repeating this process many times reduces the organized motion of the ion, bringing it to temperatures that can be far below 1/1000th of a degree above absolute zero. David Wineland and his colleagues at the United States National Institute of Standards and Technology developed exceptionally precise methods for cooling, preparing, manipulating, and measuring trapped ions. Their work helped turn individual ions into controllable experimental systems rather than merely isolated objects. A single ion can be illuminated with laser light tuned to a strong atomic transition. The ion absorbs a photon, enters an excited state, and then quickly emits another photon as it returns to the lower state. This cycle repeats many times each second. To a sensitive detector, the ion appears as a small bright point of fluorescence. The atom itself is much too small to see directly, but the stream of photons reveals its location, It is rather like identifying a lighthouse not by seeing the lamp mechanism, but by collecting the flashes it sends outward. The brightness can also reveal the ion's internal quantum state through a method known as electron shelving. An ion may possess one state that interacts strongly with the detection laser and another long-lived state that does not. While the ion remains in the cycling transition, it scatters many photons and appears bright. Occasionally the ion enters the long-lived state. The detection laser can no longer drive the usual cycle, so the fluorescence suddenly stops. The ion appears dark. When it later leaves that state and returns to the cycling transition, the fluorescence resumes just as abruptly. The change resembles a lamp being switched off and on. Although nothing visible has physically vanished from the trap, the ion remains in place. What has changed is its internal quantum state. In 1986, several research groups reported observations of this behaviour in individual trapped ions. Warren Nagorny, John Sandberg and Hans Damelt observed quantum jumps in a single barium ion. Thomas Soter and his colleagues carried out closely related work, while Wayne Etano, John Bergquist and David Wineland studied similar transitions in trapped mercury ions. The recorded fluorescence showed extended bright periods interrupted by sudden dark intervals. A single quantum system could now be followed through time. Earlier experiments had inferred atomic transitions from average light intensity or spectral lines produced by vast numbers of atoms. Here, the transition of one ion appeared as an abrupt change in the detected photon stream. The phrase quantum jump can easily create the wrong mental image. It does not mean that a tiny electron was visibly seen leaping from one miniature circular orbit to another. Modern quantum mechanics does not describe electrons inside atoms as small planets, following definite paths around a nucleus. Atomic states are represented by wave functions and discrete energy levels. A quantum jump is a transition between those states, revealed through the way the atom interacts with light. Nor does the detector observe the transition as a continuous journey through intermediate energies. It records a bright state, then a dark state, or the reverse. The internal dynamics can involve coherent evolution, spontaneous emission, and interaction with the electromagnetic field, but the measured signal separates into distinct periods. These experiments made quantum discreteness unusually immediate. The observer no longer had to reconstruct the existence of energy levels from a distant spectrum. The ion's fluorescence changed in real time as its state changed. Trapped ions have since become some of the most precisely controlled systems in experimental physics. In optical clocks, the frequency of radiation associated with a narrow atomic transition provides an exceptionally stable reference for measuring time. Some modern ion clocks would lose or gain less than a second over timescales far longer than the current age of civilization. Precision spectroscopy with trapped ions tests quantum electrodynamics, searches for tiny changes in fundamental constants, and examines whether matter and antimatter obey exactly the same physical laws. Trapped particles also support tests of fundamental symmetries. Experiments compare properties such as charge, mass, magnetic moment, and transition frequencies with extraordinary accuracy, searching for deviations that might reveal physics beyond established theories. In quantum simulation, carefully arranged ions imitate the interactions of more complicated quantum systems. Lasers control the internal states of the ions and couple them through shared vibrations of the trapped chain. These same tools make trapped ions a leading platform for quantum computation. Two internal states of each ion can represent a quantum bit. Laser pulses prepare superpositions, perform logic operations, and generate entanglement between selected ions. Because atomic ions of the same element are naturally identical, they avoid some of the manufacturing differences found in artificial devices. Their quantum logic operations have achieved some of the highest measured fidelities in any experimental platform, although controlling large numbers of ions remains technically demanding. The progress from ensemble measurements to individual trapped particles did not make quantum behaviour disappear into classical certainty. Greater control revealed the quantum structure more clearly. Isolation reduced unwanted environmental interactions. Laser cooling narrowed the ion's motion. Carefully chosen light fields prepared and measured particular states. Each improvement allowed the discrete transitions, probabilistic timing, and coherent evolution of one system to become more visible. A single trapped ion could glow steadily for a while, fall silent without moving, and then brighten again. Within those quiet changes, physicists were no longer observing only the average behaviour of matter. They were watching one quantum system reveal its allowed states, one photon at a time. Erwin Schrödinger's famous cat was never intended as a cheerful suggestion for experimental design. In 1935, Schrödinger imagined a sealed box containing a cat, a radioactive atom, a detector, and a mechanism connected to a vial of poison. If the atom decayed, the detector would trigger the mechanism. If it did not decay, nothing would happen. Quantum mechanics could describe the radioactive atom as a superposition of decayed and undecayed possibilities before measurement. If that description were extended without explanation to the entire apparatus, the cat would seem to become entangled with the atom, producing a combined state containing both a living cat and a dead cat. Schrödinger introduced the scenario to expose a problem. Quantum superposition worked extremely well for microscopic systems, but applying it directly to an ordinary object appeared absurd. Real cats are not encountered as visible mixtures of incompatible conditions. They are found in one definite state, usually accompanied by a strong opinion about the box. The thought experiment therefore raised a serious question. If quantum mechanics governs atoms, and everyday objects are made from atoms, why does the familiar world not display obvious superpositions? One way to investigate this boundary is to create quantum states whose components become increasingly distinct. A particle might occupy a superposition of two positions. A field might contain two measurably different amplitudes. An ion might possess two separated patterns of motion. The difficulty is not simply producing such a state. It must also be protected from uncontrolled interaction with the surroundings. Every collision with a gas molecule, every stray photon, every vibration, and every thermal fluctuation can carry away information. The environment does not need to perform a neat laboratory measurement. It only needs to interact differently with the alternative components of the superposition. During the late 20th century, Serge Haroche, Jean-Michel Raymond, Michel Brun, and their colleagues developed exceptionally delicate experiments in cavity quantum electrodynamics. Cavity quantum electrodynamics examines the interaction between individual atoms and quantist electromagnetic fields confined inside a carefully constructed cavity. In the Paris experiments, microwave photons were trapped between two highly reflective surfaces cooled to very low temperatures. The mirrors were designed so that microwave radiation could bounce back and forth many times before escaping. This gave atoms enough time to interact with the field in a controlled way. The researchers used Rydberg atoms, which are atoms prepared in highly excited states. Their outer electron occupies a state extending far beyond the ordinary size of the atom, making the atom unusually sensitive to weak electromagnetic fields. These atoms passed one at a time through the cavity. Their internal states could be prepared before entry and measured after leaving. Crucially, the atoms could probe the field without always absorbing and destroying the photons inside. This form of nearly non-destructive measurement allowed the same cavity field to be examined repeatedly. The atoms acquired phase shifts depending on the number or state of the microwave photons, carrying information out of the cavity while leaving much of the field intact. The group used these methods to create superpositions involving distinguishable electromagnetic field states. In simplified terms, the cavity field could be placed in a quantum combination of two different amplitudes or phases. These states are sometimes called Schrödinger cat states, because their components are more distinct than the alternatives in an ordinary microscopic superposition. The cat is not a literal animal. It is a field described by two separated possibilities that can still interfere with one another. The existence of interference is essential. An ordinary classical mixture could also contain uncertainty about which field state had been prepared. Quantum superposition is different because the probability amplitudes associated with the alternatives retain a definite phase relationship. That coherence produces interference effects that can be detected through the atoms crossing the cavity. In 1996, an experiment led by Michel Brun followed the progressive loss of this interference. The researchers varied the time allowed between the preparation and later probing of the field. At short delays, the measurements revealed clear coherence between the distinguishable components. As time passed, the interference weakened. Eventually, the field behaved more like an ordinary statistical mixture than a coherent superposition. The rate of this change depended strongly on how far apart the two components were in the relevant quantum description. More widely separated alternatives lost coherence faster. This was an experimental view of decoherence taking place. Decoherence occurs when a chosen quantum system becomes entangled with degrees of freedom in its environment. The cavity field may interact with the mirrors, residual thermal radiation, or electromagnetic modes outside the idealized system. Each environmental interaction can acquire partial information about which component of the superposition is present. That information becomes dispersed across many surrounding variables that are not measured or controlled. From the viewpoint of an observer examining only the original system, the relative phase between the alternatives becomes inaccessible. The interference terms fade from ordinary local measurements. The superposition has not necessarily been destroyed in the fundamental equations governing the combined system and environment. Instead, the coherence has spread into correlations involving an enormous number of environmental degrees of freedom. Recovering it would require controlling and reversing all those interactions with extraordinary precision. For a small, isolated system, this may occasionally be possible. For a warm, macroscopic object interacting with air, light, and its own internal particles, it is effectively hopeless. A complementary experiment was performed by David Wineland, Christopher Monroe, and their colleagues using a trapped ion. They placed one ion into a superposition involving two distinguishable components of its motion. The ion was not split into two visible chunks. Its motional wave function was prepared in a coherent combination of separated oscillatory states within the trap. The separation was large compared with the natural width of the ion's lowest motional state. In that controlled sense, the experiment created a small analogue of Schrödinger's cat. Laser pulses coupled the ion's internal electronic state to its motion, allowing the researchers to prepare and detect interference between the two components. The experiment showed that cat-like superpositions were not limited to light fields. They could also involve the mechanical motion of a material particle. The lifetime of coherence depends on several factors. Greater separation between alternatives usually allows the environment to distinguish them more easily. Higher temperature introduces more energetic fluctuations and more opportunities for information to leak away. Larger systems possess more internal components and interact with more surrounding particles. Stronger environmental coupling generally produces faster decoherence. This helps explain why quantum behaviour dominates at microscopic scales, while tables, animals, and laboratory equipment appear classical. Large objects are not exempt from quantum mechanics. They are simply entangled with their surroundings so rapidly that interference between macroscopically distinct alternatives becomes unavailable almost immediately. Decoherence provides a powerful explanation for the emergence of stable, classical-looking possibilities. It explains why certain states are robust while delicate superpositions disappear from practical observation. It does not, by itself, settle every part of the measurement problem. After decoherence, the system can be described as though it were an ordinary mixture of alternatives for most local purposes. Different interpretations still disagree about why one particular outcome is experienced. Some introduce physical collapse, others describe branching alternatives, hidden variables, or relational outcomes. Decoherence explains the suppression of observable interference, but it does not force all interpretations to agree on the ultimate meaning of a single result. Its practical importance is nevertheless immense. Quantum computers must preserve coherence long enough to perform useful operations. Precision sensors rely on interference between carefully prepared quantum states. Atomic clocks depend on protecting stable phase relationships. Matter wave interferometers require isolation from vibrations, collisions, and thermal radiation. Engineering larger quantum systems is therefore largely an exercise in managing decoherence. Researchers cool devices, improve vacuums, shield electromagnetic noise, correct errors, and design states that are less vulnerable to environmental disturbance. Schrödinger's cat began as a criticism of an unexplained boundary between quantum possibility and everyday definiteness. Cavity fields and trapped ions later allowed physicists to explore that boundary directly. The experiments did not find a sharp line where quantum mechanics suddenly stops. They found a gradual physical process through which coherence leaks outward and becomes hidden in the wider environment. The classical world does not appear because quantum rules have disappeared. It appears because those rules have spread their correlations too widely, for the alternatives to interfere in any way we can ordinarily observe. At ordinary temperatures, a gas appears to be a collection of independent particles moving in every direction. Each atom follows its own restless path, colliding with other atoms and with the walls of its container. Cooling the gas slows this motion, but under exceptional conditions, something far stranger can happen. A large number of atoms can begin to share one collective quantum state, allowing matter to behave with an extraordinary degree of unity. The idea began with Satyendra Nath Bose. In 1924, Bose developed a new statistical description of particles of light. Instead of treating photons as distinguishable objects that could be followed individually, he counted the possible arrangements of the particles in a way that respected their fundamental indistinguishability. Albert Einstein recognized the importance of Bose's method and helped bring the work to wider attention. He then extended the same statistical reasoning from photons to material particles. The particles that follow this form of quantum statistics are now called bosons. They include photons and several fundamental particles, as well as complete atoms whose total spin has the appropriate whole number value. Bosons possess an unusual collective freedom. Unlike fermions, which are restricted by Wolfgang Pauli's exclusion principle, many identical bosons can occupy the same quantum state. Einstein realized that this property should produce a new form of matter at extremely low temperatures. As a gas cools, the atoms move more slowly, and their associated matter wavelengths become longer. Eventually, those wavelengths can grow large enough to overlap significantly. The atoms can no longer be treated as separate classical particles following clearly distinguishable paths. Below a critical temperature, a substantial fraction of the atoms should accumulate in the lowest available energy state. The gas would then form what became known as a Bose-Einstein condensate. This prediction was made decades before physicists possessed the technology required to create one. The experimental difficulty was immense. The atoms had to be cooled to temperatures measured in millionths or even billionths of a degree above absolute zero. At the same time, the gas had to remain dilute. Cooling an ordinary substance usually causes it to condense into a liquid or freeze into a solid. In those dense forms, strong interactions between neighbouring particles can hide the clean quantum behaviour researchers wish to study. A Bose-Einstein condensate had to be both extremely cold and thinly spread, which is rather like asking a crowd to become perfectly coordinated while also keeping everyone politely far apart. Several major advances eventually made this possible. Laser cooling provided the first stage. Scientists including Stephen Chu, Claude Cohen-Tanuji, and William Phillips developed methods for slowing atoms with carefully tuned laser beams. An atom moving toward a beam sees the light shifted slightly in frequency through the Doppler effect. By tuning the laser just below an atomic transition, researchers can arrange for approaching atoms to absorb photons more readily than retreating ones. Each absorbed photon delivers a small push against the atom's motion. The atom later emits light in a nearly random direction. Repeating the cycle many times gradually reduces the average speed of the gas. Laser cooling can bring atoms to extraordinarily low temperatures, but it does not always reach the regime needed for condensation. A second technique, known as evaporative cooling, removes the most energetic atoms from a magnetic trap. The principle resembles the cooling of a cup of tea, as its fastest molecules escape through evaporation. In an atomic trap, researchers gradually lower the confining barrier. The hottest atoms escape, while collisions redistribute the remaining energy among those left behind. Repeated carefully, this process lowers the temperature dramatically. In 1995, Eric Cornell and Carl Wieman created the first widely recognized Bose-Einstein condensate in a dilute atomic gas at the Joint Institute for Laboratory Astrophysics in Boulder, Colorado. Their experiment used rubidium atoms held in a magnetic trap. After laser cooling and evaporative cooling, the gas reached a temperature of roughly 170 billionths of a degree above absolute zero. At that point, around 2,000 atoms entered the same lowest energy quantum state. The evidence appeared in the momentum distribution of the gas. When the magnetic trap was switched off, the atoms expanded outward. A normal thermal cloud produced a broad distribution because its atoms possessed many different velocities. The condensate produced a narrow, sharply concentrated feature within that broader cloud. A large fraction of the atoms possessed nearly the same low momentum, revealing their collective occupation of one quantum state. Soon afterward, Wolfgang Ketterle and his group at the Massachusetts Institute of Technology produced condensates using sodium atoms. Their samples contained larger numbers of atoms and allowed a wider range of experiments. One especially striking demonstration involved two separately prepared condensates. The condensates were released from their traps and allowed to expand until they overlapped. Where the two matter waves met, they produced a series of alternating regions of high and low atomic density. This was an interference pattern, similar in principle to the fringes produced by light passing through two slits. The results showed that coherent matter wave behaviour extended across entire clouds containing vast numbers of atoms. Each cloud possessed a well-defined collective phase, and the relative phase between them determined the positions of the interference fringes. A Bose-Einstein condensate is often described as a group of atoms behaving as one. This is useful, but it should not be taken too literally. The atoms do not fuse into one enormous indivisible particle. They remain individual atoms and can still interact, scatter, or leave the condensate. What they share is a common quantum state described by one collective wave function. That shared state allows large-scale quantum phenomena to emerge. Some condensates display superfluid behaviour, moving with extraordinarily little internal resistance. When rotated, a superfluid does not respond like an ordinary liquid. Instead, it can form quantacid vortices, tiny whirlpools whose circulation occurs only in particular allowed amounts. These vortices provide another visible sign that the fluid is governed by a coherent quantum phase. Researchers have also created atom lasers. An ordinary laser produces a coherent beam of photons. An atom laser releases a controlled beam of atoms from a condensate, while preserving much of its matter wave coherence. Although atom lasers are less familiar than optical lasers, they offer possibilities for precision interferometry, navigation, measurements of gravity, and sensitive tests of fundamental physics. Ultracold gases also serve as highly adjustable models of other quantum systems. Researchers can change the strength of atomic interactions using carefully controlled magnetic fields. They can confine atoms to extremely thin layers or narrow tubes, creating systems that behave as though they have only two dimensions or one. Optical lattices, formed from intersecting laser beams, create repeating landscapes in which atoms can move between artificial sites. These arrangements imitate some of the physics experienced by electrons inside crystalline materials. Because the atomic interactions and geometry can be tuned, physicists use ultra-cold gases to explore quantum phase transitions, magnetism, superconductivity, and strongly interacting matter under clean laboratory conditions. Some of these systems are extremely difficult to calculate directly with conventional computers. The atoms effectively perform part of the quantum problem through their own behaviour, creating a form of analog quantum simulation. Bose-Einstein condensates have also supported precision measurements of acceleration, rotation, and gravitational fields. Their long matter, wavelengths, and high degree of coherence make them useful for atom interferometers, capable of detecting extremely small changes in motion. The achievement was conceptually as important as it was technical. Quantum wave behaviour had once been observed through individual electrons scattered from crystals. It could now be organised across a cloud of atoms large enough to image. The condensate remained tiny by everyday standards, but it stretched across distances vastly greater than the dimensions of one atom. Thousands or millions of particles could share a collective phase, interfere as matter waves, and respond together as one quantum system. Matter had not ceased to consist of atoms. Instead, the distinctions between those atoms had become less important than the state they shared. At temperatures almost unimaginably close to absolute zero, a thin gas could therefore abandon much of its ordinary restless individuality and settle into a quiet form of collective quantum behaviour. For much of the 20th century, quantum physics was treated mainly as a theory to be tested, interpreted, and occasionally argued over. Superposition, entanglement, and measurement seemed like peculiar features of nature that physicists had to accept, even if their deeper meaning remained unsettled. Gradually a new question emerged. Instead of asking only what these quantum effects meant, researchers began asking whether they could be controlled. Could superposition store information? Could entanglement connect distant systems? Could the restrictions imposed by quantum mechanics become useful rather than merely inconvenient? This change in perspective helped create the field of quantum information. A quantum state can contain more information than one ordinary measurement can reveal. Consider the polarization of a photon. A photon may be horizontally polarized, vertically polarized, or prepared in a superposition involving both possibilities with a particular relative phase. One measurement produces only one outcome. It cannot reveal every amplitude and phase contained within an unknown state. Repeating the measurement would not help unless many identically prepared copies were available, because the first measurement generally changes or destroys the original state. Quantum mechanics also places a deeper restriction on copying. The no-cloning principle states that an arbitrary, unknown quantum state cannot be copied perfectly, while the original remains intact. This is not merely a limitation of current technology. Perfect cloning would conflict with the mathematical structure of quantum mechanics. A machine might copy a known set of states, but it cannot duplicate every possible unknown superposition with complete accuracy. Quantum teleportation provides a way to transfer an unknown quantum state without first learning every detail contained within it and without creating an additional perfect copy. In 1993, Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Josser, Asher Perez, and William Wouters described the first complete quantum teleportation protocol. Despite its name, teleportation does not transport matter instantly from one location to another. The physical particle carrying the original state remains where it is. What is transferred is the quantum state itself, reconstructed in another physical system. The protocol requires three essential resources. First, the sender and receiver must share an entangled pair of particles. One member of the pair remains with the sender, while the other is delivered to the receiver. Second, the sender performs a joint measurement involving the unknown state and the sender's member of the entangled pair. This is known as a Bell state measurement. The result does not reveal the full unknown state. Instead, it produces one of a small number of possible outcomes. During this process, the original local state is no longer preserved in its previous form. Third, the sender communicates the measurement result to the receiver through an ordinary classical channel. Once this message arrives, the receiver performs the corresponding operation on the distant member of the entangled pair. That particle then takes on the state originally held by the sender's particle. The original has been destroyed locally, and the state has been reconstructed elsewhere. This is essential. Teleportation cannot be used to manufacture unlimited copies while keeping the original safely on a shelf. In 1997, Dick Basmeister, Jan-Wei Pan, Klaus Mattel, Manfred Ebel, Harold Weinfurter, and Anton Zeilinger carried out a landmark photonic teleportation experiment in Innsbruck. Their apparatus used entangled photons and carefully arranged optical components. The polarization state of one photon was transferred to another photon through a partial Bell state measurement and the correlation supplied by entanglement. During the same period, Daniele Boschi, Salvatore Branca, Francesco De Martini, Lucian Hardy, and Sandu Popescu reported closely related optical work demonstrating important elements of the teleportation process. These experiments were technically delicate. Photons had to be produced synchronized, directed through beam splitters, and detected in the correct combinations. Many trials failed because particles were lost or the required coincidence did not occur. The successful events nevertheless agreed with the quantum predictions. Teleportation does not allow usable information to travel faster than light. Before the classical message arrives, the receiver's particle appears random. The receiver cannot identify the teleported state or use it to extract a message. Only after learning the sender's measurement result can the correct operation be applied. The classical communication therefore remains limited by the speed of light. Entanglement supplies the quantum connection, but it does not remove the ordinary causal limit. Quantum information also led to the idea of entanglement swapping. Two particles that have never directly interacted can become entangled when suitable joint measurements are performed on their partners. This provides a possible route toward quantum repeaters. Directly transmitting entanglement across great distances is difficult, because photons are absorbed and scattered. A quantum repeater would create entanglement across shorter sections and connect those sections through entanglement swapping. The broader field now includes quantum cryptography, quantum networks, quantum error correction, quantum sensing, and programmable quantum processors. Quantum cryptography uses the disturbance associated with measurement to reveal certain forms of interception. Quantum sensors exploit coherence and entanglement to measure time, magnetic fields, acceleration, and other quantities with exceptional sensitivity. Quantum error correction protects fragile information by distributing it across several physical systems without violating the no-cloning principle. Quantum processors use controlled superposition and entanglement to perform operations that cannot be described as independent classical calculations on each component. Considerable obstacles remain. Quantum states are vulnerable to noise and decoherence. Photons are lost during transmission. Detectors miss particles. Gates and measurements are imperfect. Expanding a carefully protected experiment into a large, dependable system requires error rates to be controlled across many connected devices. Yet the historical change is already profound. Entanglement began as a challenge to the completeness of quantum mechanics. Superposition appeared as a strange mathematical necessity. Measurements seemed to create awkward conceptual puzzles. These same features are now prepared deliberately, manipulated with lasers and microwave pulses, transmitted through optical fibers, and preserved inside experimental processors. Quantum strangeness did not disappear when physicists learned to control it. It became a resource. Ideas once used mainly to debate the meaning of reality had entered the laboratory as tools, allowing quantum information to be stored, transferred, protected, and increasingly engineered. The quantum experiments that changed everything did not reveal one isolated oddity. Together, they replaced the classical picture of continuous energy, definite trajectories, separable objects, and passive observation with a framework built around quantization, probability amplitudes, superposition, entanglement, and physical measurement. Blackbody radiation introduced the first quantum of energy. The photoelectric effect showed that light transfers energy in individual packets. Atomic spectra and the Frank-Hertz experiment revealed discrete energy levels, while Compton scattering established that photons carry momentum. Stern-Gerlach beam splitting exposed quantized spin, and electron diffraction and single particle interference demonstrated that matter follows wave-like rules. Other tests showed that quantum physics succeeds not only through dramatic patterns, but through tiny numerical differences. The Lamb shift and the electron magnetic moment confirmed quantum electrodynamics with extraordinary precision. Quantum behaviour then expanded into objects large enough to manufacture and control. Superconductors carried persistent currents. Josephson junctions displayed tunneling and interference. Trapped ions revealed individual quantum jumps, while cavity fields, Schrödinger cat states, and Bose-Einstein condensates made coherence visible across increasingly large systems. Bell experiments produced one of the deepest conclusions, ruling out the tested class of local hidden variable explanations without permitting faster-than-light communication. Delayed choice and quantum eraser experiments showed that measurement context and correlations matter, but they did not allow information to travel backwards through time. Quantum teleportation completed another transformation, turning superposition and entanglement from conceptual mysteries into practical resources for communication and information processing. No single experiment created quantum mechanics. The theory became unavoidable because many unrelated experiments using different materials, instruments, and physical principles repeatedly revealed the same underlying structure. Questions remain about the wave function, definite outcomes, measurement, and the boundary between quantum and classical descriptions. Yet the quantum world is not distant from ordinary reality. Its experimentally tested rules govern atoms, chemistry, materials, light, electronics, stars, biological molecules, and the physical structure of everything around us.